Hey everyone, and welcome back to Prefusion. I'm Anish, and today we'll be solving the most important gate PYQs from the frequency response analysis topic. The frequency response analysis topic contains mainly four chapters: Bode plots, Nyquist plots, polar plots, and frequency response of second order systems. So we'll solve all the important PYQs from all of these four topics. If you want more chapters, other topics from control systems, then show your support. Hit the like button. That will make me understand, yes, you are liking the content and you want more content like this. Then I will try to bring more practice PYQs, right? So yeah, that is one thing. And yeah, we'll straight away start with Bode plots. We have been given a transfer function, and the value they have asked us to find the values of constant gain term and the highest corner frequency of the Bode plot. So what is the constant gain term here? So constant gain term, they mean by constant gain term is this k term, but here, like, this is not in time constant format. So definitely this 5 is not equals to my constant gain term. So in the option also 5 is not given. Like, this 5 is for the highest corner frequency, not for the constant gain term. So first thing what you should keep in mind is k is this constant gain term, k is not equal to 5. Okay, why? Because transfer function not given in time constant format. Okay, this is the first thing. So we have to convert it into time constant format. So let's convert it. But before that, like, what other thing can you notice? Like, they have asked for the highest corner frequency. So for finding the highest corner frequency, obviously you will need the location of the poles. So here, what is the location of the pole? 0.25. Here the pole location is 0. So obviously these two are there, but we have to check the location of the poles here. Okay, so check location of poles. Now what you can do is, what you find here is that, like, whenever this type of format is given, like s square plus a s plus something, okay, some constant number, then you always check whether the roots are complex conjugate or not. How do you check that? Basically you check the discriminant of this quadratic equation. So just by seeing this you can do this. You don't need to write anything. What you do, b square minus 4ac should be greater than 0 for it to have real and distinct roots. It can have equal also if this is like b square minus 4ac equals to 0. Okay, let's see. So b square is 4 minus 4ac minus 100. Sorry, b square is 16 minus 100, which is something negative, minus 84. So under root of negative 84 will be something imaginary. So you will get complex conjugate root. So here, like, just by seeing that, I'm seeing that this we get complex conjugate root. Okay, we get complex conjugate root. And what are the real part? The real part will be minus b upon a, which is minus 4 itself. So real part will be on the minus 4. Okay, so here this one 4s plus 25, the discriminant, like, this is equals to 0, so the discriminant d equals to b square minus 4ac. Okay, so what is this equals to? This is simply equals to 60 minus 100, simply equals to minus 84. Okay, minus 84. So the discriminant is equals to minus 84. So definitely, like, from here we can understand we will get complex conjugate roots. So whenever complex conjugate roots, let me write this. Conjugate roots. So, and like, so what we'll do, we'll assume, like, the this format should be this, that it should be s square plus 2 zeta omega ns plus omega n. Then what we do, whenever we get complex conjugate root, then assume corner frequency at omega n. So here I'm assuming corner frequency at omega n and slope after omega n equals to minus 40 dB per decade. Okay, equals to minus 40 dB per decade. So slope after omega n is equals to minus 40 dB per decade. Now this is about the omega n, right? So now what you can do is you can simply take common omega n and like then what will be my corner frequency, highest corner frequency? So sorry, this is I have to do one thing, sorry. Yeah, so what is omega n square here? Omega n square here is 25, right? Omega n square is 25 because this format is matching. Okay, coefficient of s square should be 1 to keep this in mind. So and this is 25 and omega n equals to 5 itself. Okay, so omega n equals to 5 itself. Okay, so these are the things. Now what else? So basically omega n we got. So this is the highest corner frequency from here. So 5 will be the highest corner frequency. So either option A or option D will be correct. These options are eliminated. So now what about my k, value of k? So for value of k, what you can do? Simply take what we used to do. We should take common the omega n itself. Omega n we should take common. Okay. So from the equation, okay, where is the equation is not present? So what I will do? This is 5. So now we'll convert g of s into time constant format. G of s into standard time constant format. Okay, so what do we do here? So basically so we have 5 over here, and also like I have to take common s4, right? I have to take common 4 here, take common 4 over here. So this will be times 4 s by 4 plus 1 divided by s into 0.25 into s divided by 0.25 plus 1. Now what do we do? Here we take omega n square common. If you remember, we normally say omega n square. So we'll take common as omega n square. (25) common, and this will be s square divided by 25 plus 4 by 25, and this will be 1. Okay, this is how we convert it, if you remember correctly. So now just simply like what we will do, this 5 will get cancelled with this, so we'll have 5 here, and this is 1 by 4. 4 will get in the numerator, so this is 16 by 5 itself. So what do you get? This is 3.2. okay, and this is equals to k, k, right? So I will just copy this. Equals to k. So this is equals to k. So basically this is equals to k, right? This is equals to k. So like one more thing. So 3.2. So what is the option? 3.2 and 5. So option A is correct. Okay, option A is correct. So I should write here like my corner frequency. Like I assume corner frequency is here. Okay. So basically how, like any other method, like without the discriminant, can you do it? So basically what you could have done is you could have found the zeta also. Okay, you compared this with that equation, you found out omega, and like you assume that you have got complex conjugate roots, you write omega n square, then you write then you find like zeta. Then you find zeta. So how will zeta look like? No, you need to assume complex conjugate poles. This is valid for all of them, right? This is valid for all of the type of second order system. So you just compare this with omega n square, and then you put omega n in this equation. So 2 zeta omega n equals to what? 4. Equals to 4. So now if you put this equals to 4, your zeta will be, so this omega n is 5. So 10.4. Zeta is 0.4. That means my zeta is 0.4. That means it is lying between 0 to 1. That means I have complex conjugate poles. Complex conjugate poles. Okay. So yeah, this is the question basically. So let's swiftly move to the this question, this lecture. Basically this is same, only I forgot to tell you that here in this lecture also we'll do mainly questions. Okay, mainly whatever we have studied till now we'll just revise. So this is a very interesting question, recent question, gate 2016. Either you can do it in seconds or it will take you very high time if you don't know about the concept of Bode phase plot. So here we have been given an asymptotic Bode phase plot. Okay, and this is written like k by s plus 0.1, s plus 10, s plus p1. Fine. With k and p1 both positive. K and p1 are both positive. Okay, they want us to find the value of p1. How will you find the value of p1? So what we have to notice is that two roots are given, two poles are given. Okay, one is we have to find out. So if this is given, okay, we don't care about the k term, okay, and don't care about the constant time constant format, because we are not plotting the Bode gain plot. We are concerned with the Bode phase plot. So in that we don't care about the gain and stuff. So we are only concerned with the corner frequencies. Okay, so here we have a pole at s equals to 0.1. What does this means? This means 10 times before 0.1 and 10 times after 0.1, the slope should be minus 45 degree per decade. So 10 times before 0.1 is the slope minus 45 degree per decade. Here if I see, I am moving from 0.01 to 1, moving 45 degrees. That means in 1 decade I am traveling minus 45 degrees. So it is minus 45 degrees per decade. What does, so this is satisfying. What about this? 10 times after this should also be minus 45 degree per decade, but from the line itself, from the slope itself, we are seeing that slope is further increasing in the negative direction. That means it is not minus 45 degree per decade, but still we can cross verify. In 1 decade, okay, from 0.1 to 1, it is traveling from minus 45 to minus 135. That means it is traveling to minus 90 degrees. So in 1 decade it is traveling 90 degrees. 1 decade traveling 90 degrees. Okay, so yeah, that means what is the slope? Slope is minus 90 degree per decade. But should it be 90 degree per decade if only this pole was like present around this region? It should be minus 45 degree per decade, but it is minus 90. So definitely something has changed. Some pole has been introduced because the slope has further decreased. Okay, also let's check for s equals to 10. Now at s equals to 10 times after this and 10 times before this, the slope should be minus 45 degree per decade, only due to this pole I am talking about. Okay, so 10 times after this, my slope is here I am going 1 decade, and in the y-axis I am traveling minus 45. That means, okay, 10 times after this I am getting minus 45 degree per decade. That means like this slope is only influenced due to this pole. So in this region I have only this pole. That is what this slope is telling me. But if I travel from 1 to 10, again my slope becomes minus 90. You see, okay, 1 decade I am traveling and I am traveling 90 degrees in the negative direction. So my slope is minus 90 degree per decade again. So what is this telling me? This region is telling me I have another pole around here. I have another pole around this region, which is contributing to further minus 45 degree per decade slope. So this is contributing minus 45 degree per decade, but another pole is there somewhere in this region which is contributing another 45 degree per decade. Where is the pole? Now either you can guess or you have understood by now that this 1 decade and this 1 decade is total 2 decades, and this two decades my slope is further getting reduced by 45 degrees. That means between these 2 decades here I will have another pole. If I have another pole here, now if I travel from 0.1 to 1, this pole will contribute minus 45 degree per decade, and this pole will also contribute minus 45 per degree decade in this region. Now I am around here, okay, around here, and like if I travel from here to here, if I have pole here, so this pole is contributing minus 45 degree per decade, and this pole is also contributing minus 45 degree per decade. So definitely this is minus 90 degree per decade. So definitely I have a pole at 1, so definitely P will be 1, because nothing else points are given, right? No other points are given anyways, but still, like from here you can understand intuitively that my pole will be 1 radian per second, P1 will be 1 radian per second. So this is just by seeing the question. You can solve this just by seeing the question. Now if you don't want to solve this just by seeing the question, now let's write things down. So now what do you observe is that observations but okay. So what observation I see? So like I have a pole here, omega P1. So this is what is this? Oh, this is P1. Okay, so let me name this as omega P2. Pole 0. This pole will affect till 0.01 to 1. Okay, that is the range of this pole, due to which what slope I will get? I will get minus 45 degree per decade. Okay, and due to this, like the this pole, this will be 1 to omega P3 100. This will be another minus 45 degree per decade. Okay, so these are the ranges. Now obviously in the graph, what I am seeing, in the graph I am seeing that my slope is, like before this 0.01 it is 0. Okay, hence before this 0.01 it is 0. So obviously this P2 is the minimum pole. Okay, minimum pole. And after between this 0.01 to 0.1, my slope is between 0.01 to 0.1, my slope is minus 45 degree per decade. That is fine. So this range is matching. Okay, this range is matching. But after this, what is happening? After the 0.1 to omega to how much? To almost 10. Almost 10. Okay, not almost 10, exactly 10. My slope is minus 90 degree per decade. Okay, so this is my slope. Okay, this is my slope. Now what does this mean? This means I have a pole around here, right, like which is getting affected by 0.1. So since 0.1 the pole is getting active, so obviously if the pole is getting active here 0.1, obviously 10 times after this my actual pole will lie, because the slope gets activated 10 times before that. So pole will lie 10 times after this. Okay, and like from this also you will understand that 1 to 100 it is telling me minus 45, but I am going till 10 minus 90. So obviously like between 1 to 10, I am getting minus 90. That means that 10 times before this 10 I have a pole here. Okay, 10 times before this and 10 times after this, because just here my pole like slope reduces from minus 90 to 45. That means the pole gets deactivated, the effect of pole gets vanished. So just after this effect of pole gets vanished, so 10 times before this my pole will lie. So yeah, This you can understand, so I'm not explaining it further. So like from here we can understand. Let me just write after 0.1 radian per second, the effect, the slope reduces further by minus 45 degree per decade. That means there is a pole at 0.1 times 10, which is radian per second, 1 radian per second. Okay, now just this is the same thing. Just what we'll do, what we'll write is after 10 radian per second, the slope reduces, increases further. The slope increases further by plus whatever degree per decade. Actually, this should be per decade. Okay, so 45 degree per decade. So this is the case. So here what does this mean? There is a pole at 10 times before 1 radian, this 10 radian per second, right? So 10 times before this. Now luckily both of them come at the same location, or else there would have been like the calculation would have been difficult, definitely. So yeah, 10 they will give some easy calculation only. So obviously from these two cases I can cross verify that my pole omega p1 will be equals to 1. P1 will be equals to 1. Okay, don't write P1 as minus 1 because they have already given what P1 is as plus P1 they have given. If they would have given as minus P1, then you would have written P1 equals to minus 1. Just be careful. So P1 will be equals to 1. Okay, so yeah, this is my answer for this question. Okay, so now let's go to the next question. What is the next question? So here we have the question that the asymptotic Bode plot of transfer function of k divided by 1 plus s plus a is given in the figure. The error in phase angle and dB gain at frequency of 0.5 e. Okay, so this time, like, this is the asymptotic Bode, but they have already given it. Although you could have drawn it by yourself, but they have given it. But they want you to find the error at 0.5 a, not at corner frequency, not at corner frequency. They want you to find the error at 0.5 a, here, somewhere around here. Okay, so obviously error for phase won't be 0. Okay, and error for this won't be simply minus 3 into n, because what is happening here, they haven't told us to find for corner frequency. So that's why I generally don't recommend mugging a formula, because if you just mug a formula that yeah, error for this gain plot is minus 3 into n, error for this phase plot is 0, but that is at the corner frequency. But they have they asked at the corner frequency? No, they have asked some frequency which is not equals to corner frequency. So keep this in mind. So omega equals to phi not corner frequency. Okay, so yeah, So like then what is my what is my error? Error is actual minus approximate value. Okay, so let's write this down, or what we used to do. Yeah, it was actual minus approximate value, or I forgot like what we used to define like the error. Was it approximated minus actual, or what was it? I written it here, right? Yeah, actual minus approximate. Let's see like the previous where I was defining my error. Was there something wrong? Yeah, here actual minus approximate, so I was correct. Okay, so it is actual minus approximate. If it is actual minus approximate, okay. So obviously like what is the actual value? So actual value, you just you have been given the transfer function, you just simply write it like that, g of j omega. They want us to find in, okay, they want us to find in dB, so we'll obviously convert everything in dBs. Omega equals to 0.5 a, this is k by under omega by a square plus 1. Okay, now this is like you put 0.5 a here, this is 0.25 plus 1 under root. Okay, so now you convert it into dBs. So if you want to convert it into dBs, so obviously what will happen, this is ratio of two numbers, so this is 20 log k minus, now this is like power half, so what you can do is like this is 20 log under root 1.25. okay, so basically like the value of this, let me calculate this one, 1.25 under root and log into 20 is almost 0.97. okay, so this will be basically the error. So this is 20 log k minus 0.97. okay, so this is minus 0.97, and now what is the approximate value? What is the approximate value? So approximate value you can see from the graph itself, or you know already, like before corner frequency this will be constant, like this is 20 log k simply. So g of approximated g omega at omega equals to 0.5. okay, so iske like sorry, I was just talking Hindi. Then what my approximate value, it is 20 log k. okay, base 10 is there. okay, I'm not writing base 10. So like let's find the error in dBs. okay, will be simply this this one subtracted by the other one, so this is here. okay, so this will be equals to minus 0.97 dBs. okay, so this is my error, this is my error. okay, this is my error. Now like in the option, like let's say in the option if plus 0.97 is given, obviously you will tick that. okay, if minus 9.97 is not given and only plus 0.97 is given, you can tick that. okay, just check if it is not MSQ or something. If it is simple MCQ, yeah, you can tick that. But sometimes what they happen, they just want to know the magnitude of the error or something, right? That's why like this sign doesn't matter to them much. Sometimes happens, like if negative isn't there in the options in MCQ, then you take plus 0.97. Now let's find the error in phase angle. So error in phase, again let's write the angle like angle formula. It is simple, right? Tan inverse minus tan inverse omega by A. So what is this? 0.5. So minus tan inverse 0.5. Okay, like this is at omega equals to omega 0.5 A. So 0.5 tan inverse. Okay, what? Yeah, this is in degrees. What am I doing? Something wrong? Something is wrong. 0.5. Yeah, 26 point. I told you guys to remember. Okay, this formula I told you guys to remember, like tan inverse 2 and tan inverse 1 by 2. They're just simply 90 minus of each other. So this will be minus 26.56 degrees. Okay, now let's find the angle here. Now the angle isn't simple anymore. Why? Because this is changing and I have to find in between. Okay, so like we can use the formula as this is not simple linear scale. We just simply can't use that y equals to mx formula. That we can't use. Okay, just be careful. This is not a linear scale. So we have to use that slope formula in the log scale. Okay, in the log scale we have to use. Okay, so in the log scale if you use, what will happen? So what is this value? This is like minus 90 because it is going from 0 to 2 decades, so it will be minus 90 here, but we don't care about that. We know this is 0 degrees. They haven't mentioned it, but they should, like, this is 0 degrees. Okay, this is 0 degrees. This is important. So now what you do is 0 degrees, you simply use a slope formula. So let me mark few points here. This is A and this is B. So slope A comma B equals to YB minus YA divided by log of omega B by omega B by omega A. Okay, so like YB we have to find out here. YB you have to find out, and this B location is at 0.5 A. So YB definitely you have to find out. So this is YB minus YA is 0, and this is log of, again this is like 0.5 A2 divided by 0.1 A, so which is log of 5 itself. 5, base is 10 and slope is minus 45. So minus 45 into log base 10 of 5 equals to my YB, because YA is 0. So this is equals to my approximated angle G of J omega at omega equals to 0.5 A. Okay, so basically what is happening over here? So basically my angle of G of J omega at omega equals to 0.5 A equals to, like, what is log 5? What is log 5? Log 5 is 0.69 times minus 45, simply equals to minus 31. Okay, pretty close, but still there is some error. Minus 31.4536 degrees. Okay, so this is my log 5 basically. So this is the value of approximate value. So what is the error? What is the error basically? So error equals to actual 26, like this is minus 26 minus 26.56 minus of 31.4536. So what is this equals to? Plus, okay, 26.56 almost equals to 4.9. okay, almost equals to 4.9 degrees. So my answer will be 4.9 here. Okay, so yeah, my answer will be this 4.9 degrees. This is the first second answer, and this is the this answer. Okay, two answers, 4.9 degrees and 0.97 degrees. Okay, so yeah, these are the two answers basically. So this is it for this question. Let's move on to the next question. So let's see this question. This is also a a gate question, but I have forgotten to write the year. So here what does this tell us? So here they have given us the gain and the phase angle. They have given us the gain and the phase angle of a stable transfer function. The Bode magnitude and phase plot of a stable transfer function is given. They haven't told us about anything about the coefficients of S or something. They have given this, that consider the negative unity feedback configuration with gain k. This is the negative unity feedback configuration in the feed forward path. Fine. The closed loop is stable for what value? Okay, is stable for what value? The maximum value of k naught is what? So here what do you observe is that currently what are, they haven't given us anything here, they haven't given us anything here, everything no, only this graph is given and few information in the graph is given. So obviously we'll decode few information from the graph itself. Okay, so information from graph. Okay, obviously you will do this much faster when you know which information to take and which information to ignore, but for now we don't know which information to take and ignore. After solving this question, after solving many questions, you will understand which ones to ignore and which ones to take. Okay, information from graph. So here if you see that what is the information here, the information here is they have given us the phase at this particular frequency, and the same frequency they have given us a gain. And what is the phase here? Phase is minus 180. So if you know the phase here, what is this called? Like when at what frequency is my phase minus 180? It is the phase crossover frequency. So at omega pc they have given me the gain, but they haven't given me the omega pc, but they have given me the gain at phase crossover frequency. So okay, what is it? It is equals to 20 dBs. It is equals to 20 dBs. Okay, what else they have given me? So here they haven't provided me the frequency at which the function reaches 0 dBs, or it is also known as the gain crossover frequency. They haven't provided me. Also they haven't provided me the phase also. So okay, where did it go? They also haven't provided me the phase also. Okay, so yeah, we'll obviously we don't know that. Now what else they have provided me? They have provided me the DC gain also, because they have provided me the low frequency gain, which we'll assume as DC gain, because we don't have any poles or zero at the origin. So provided me the low frequency gain, frequency region gain, as no poles and origin are present. Okay, that means it will be simply equal to DC gain. Okay, DC gain, so which is simply equals to N naught by D naught. Okay, you put G of S equals to 0 over here, so obviously all this will get cancelled, only N naught by D naught will be remained. So this is equals to what? This is an absolute scale and they have provided us in dB scale. Okay, so dB scale is 36 dBs. 36 dBs. Now you convert this into absolute scale. Okay, simply equals to 20 by 36 is to 1.8, which is 10 raised to power 1.8. So it is 1.8 itself. Okay, 1.8. Okay, so it is 10 raised to power 1.8. So N naught by D naught is 10 raised to power 1.8. Now is this information even useful? We will see. 10 raised to power 1.8. Okay, now what is this value? Let me calculate this. It is 63 63.1. Okay, it is 63.1. So n0 by d0 equals to 63.1. Okay, so these are the two information that I know from the graph. Now what they are telling us is we have to find the maximum value of k0 for which system is stable. Now is the system stable right now? Is the system stable right now? So here how can you identify if the system is stable or not? So what you can do is that, what is this frequency called? Phase crossover frequency. You put phase omega pc over here. Okay, omega pc over here and omega gc over here. Okay, now I told you one condition, right? If you recall correctly, that your phase crossover frequency should come later for stability. Okay, your phase crossover frequency should come later for stability. Like phase your omega pc should be greater than omega gc. Okay, this was one condition for stability. Okay, for stability your omega pc must be greater than omega gc. Okay, so is it the case here? It isn't the case. Like from here I can understand that my system is unstable. Currently it is unstable, but with the variation of k I can make it stable. But is this true really? Let's check. So let's check the gain margin right now. So we know the gain at this. So what is the gain margin? The gain margin is simply equals to 1 by magnitude of this transfer function omega pc, which is in dBs, it is in terms of like minus magnitude of g omega equals to omega pc in dBs. This is in dBs. So like what is this currently? Currently this is 20. So my gain margin equals to minus 20 dBs. Now what we know in dBs for stability, my gain margin should be greater than 0, which is not the case here. It is less than 0. So definitely it is unstable. Currently unstable. But we want to make it stable. How to make it stable? So what I am doing is, what is this doing? Simply multiplying k with this magnitude. Okay, k is real. Okay, so simply multiplying k with this magnitude. So obviously this one will become k over here, k times this. So my gm currently will be simply magnitude of k, g of j omega equals to omega pc. Okay, so now like in terms of log, how can I write it? In terms of log, this will be simply minus 20 log k. K will come outside. Okay, because k is real and positive, k will come outside. Minus 20 log k, and the same thing only. Like what is this value? This value is this. Okay, and this is in 20 dBs. This is 20 dBs. Okay, this we know from the graph. So this is 20 dBs. And this is also in dBs. I won't write dB anymore. From graph. Okay, so now this is this. So what happens over here? So for this has to be positive. For my system to be stable. Okay, so obviously this has to be greater than 0 for stability. Minus 20 log k minus 20 should be greater than 0 itself. So obviously log 10 base k should be greater than minus 1 here. So this equation becomes k should be greater than 10 raised to a minus 1, which is k should be, okay, what did I do wrong here? Just what to say, k should be greater than 0. Okay. Yeah, I was doing the silliest mistake in inequalities. Actually here we have to take care. What we have to take care is, like, never just divide by something which is negative. In the inequality case, what happens? The sign of inequality changes. So I was also forgetting the same. So here, like, just shift this minus 20 over here. Okay, minus 20 log of k greater than 20 itself. Okay, fine. Now this is fine. But what else you do? Now you don't divide by minus 20, you multiply by minus 1 by 20 on both sides. Now if you multiply by minus 1 by 20 on both sides, you're multiplying by something negative, so the sign of inequality will change. So very important step, that multiply this equation with minus 1 by 20. So here sign of inequality will change. Okay, so obviously this one will become like log of 10k will be less than minus 1. Okay, because we're multiplying by something negative, so sign of inequality will change here. So this is 10 raised to k should be less than equals to 10 raised to power minus 1, so k should be less than equals to 0.1. Okay, so this is equals to my k naught, this is equals to my answer, this is equals to my k naught. Okay, so this is how you can do it. Or what you can do is, like, you convert this into absolute values, then you do that. Okay, how to do this in absolute values? So this is in dB scale, so k will be equals to 0.1. This is the answer, so 0.1 will be answer. Okay, 0.1 will be answer. Now let's do this in, like, this is in dB scale, let's do this in absolute like a decimal scale. Same thing only, right? Just for the people who don't who are a bit confused in the dB scale, they can, like, try this one out also. So in absolute scale, so what is happening? Magnitude of g of j omega at omega p, we know omega equals to omega p, we already know. What is it? It is simply equals to 20 dBs. Okay, and what is the absolute form of 20 dBs? It is what? 1, because, like, 20 divided by 20, like, it is actually equals to what? 20 divided by 20, 10 raised to power this, so this is 10 itself. So obviously this is equals to, sorry, this is not 1, so this is 10, this is 10. Okay, so this will be equals to 10. Okay, in absolute terms. Now like, what is my this magnitude of k times g of j omega at omega equals to omega p? It is 10k simply. Okay, now what is the gain margin? Gain margin is simply 1 by magnitude of g of j omega at omega equals to omega p, or omega pc you can say. Okay, omega pc you can say, whatever. So this is equals to 0.1 by k. Okay, so yeah, this is this. Now, like, just 10k, so this has to be greater than 1. Now this is an absolute scale, so this has to be greater than 1 for stability, so here, right, we don't have any negative ka chakkar. So yeah, this is, like, one good thing about this. So, like, you can cross verify if you want. Okay, so so my k will be simply less than 0.1, directly you can get from the absolute value. Okay, so, like, here we didn't need this information, the n naught by d naught. Okay, in some questions it may be needed, it may not be needed. Okay, now slowly by solving questions only you will understand when, like, you need to write this or you don't need to write this. Okay, slowly by solving questions you will understand. So yeah, this is the, like, from this is the 2 methods you can do with absolute scale, also with dB scale. Also dB scale, the problem of negative comes up because everything is in algebraic sums, but in absolute scale, like, it is in multiplication, so obviously the inequality, like, that problem won't come, so that is why. So yeah, that is one thing. Now let's solve this question. This is the last question of Bode plots basically. So here the transfer function, we have to find the transfer function from the Bode plot. So this is the first question, and find the, so I should write, like, find the find the transfer function from the given Bode plot, magnitude plot, and find the error at the corner frequency. So to find the error at the corner frequency. So here, like, what is the corner frequency here? Do recall? Is the slope changing over here? No. The slope, is the slope changing over here? No. Even like the frequency is also not given. So corner frequency is here only. Slope is changing over. We have to find the error for this corner frequency and the magnitude. Now, as zeta is given, so the error formula will be different here. The error formula will be different here. Do keep that in mind. So zeta is given, the error formula is different. Okay, like we are observing that suddenly my slope is changing from 20 dB per decade to minus 20 dB per decade. Okay, so minus 40 dB per decade, 2 poles at this corner frequency. So zeta based system, second order zeta based system, simple. But what other thing I'm noticing, like what to find the transfer function. That's why I'm telling you all this, that I have a 0 at the origin also. Initially my slope is plus 20 dB per decade. So initial slope is plus 20 dB per decade. Okay, initial slope is plus 20 dB per decade, and after this corner frequency it becomes minus 20 dB per decade. Okay, so like corner frequency zeta based system, so is 2 radian per second, and from here we can find the information about omega n. Omega n is 4. Okay, sorry, yeah, omega n is 2 itself. Sorry, omega n is 2 itself. So because like for zeta based system, omega n is corner frequency itself. So this is one thing. Okay, initial slope is there. So like initially, like I will have something like this, ks, fine. Okay, then due to this, like the slope is minus 40 dB, like slope change in slope, delta slope per decade. Okay, okay, so my slope is minus 40 dB per decade. So this is the slope. Now like can we approximate it? Like what is the order? So zeta they have given 0.6. So obviously I can write the characteristics equation from this. So it will be s square plus 2 zeta 0.6 into omega n 2 s plus omega n square 4. So this is s square plus 2.4 s plus 4. So this is one of the like terms, and this is one of the terms, and yeah, these are the only terms. Okay, so like let's write the transfer function. So obviously the transfer function k times s. So let me write this in better format. So this is like, let me write this in the time constant format. So this will be s square divided by 4 plus 0.6 s plus 1 equals to 0. So if I write this in time constant format, s square plus 4 okay, this is equals to 0.6 plus 1. Okay, so yeah, now like what is the value of k over here? What is the value of k? So the value of k you can understand from here, right? 0.1 they have given me the gain. Okay, so simply the magnitude of j omega at omega equals to 0.1 is minus 20 dB. Like minus 20 dB is what? Minus 10. Okay, sorry, minus 1 by 10. 1 by 10. Okay, like let me write here minus 20 dB, that means 10 raised to power minus 1 simply. Okay, so like what is this expression? So obviously this s will come here, but this can get ignored because like 0.1. So 0.1 whole square, like what we're doing, magnitude, right? So this is 0.6 into 0.1 whole square, and this one also. So like we're squaring, so these are getting ignored, you know. So put s equals j omega and write the magnitude expression and put 0.1. You will see that all these are getting ignored, only one is getting left out. So we'll get k will be equals to 0.1, like k into s is like k into j omega, magnitude is k into omega. So 0.1 divided by 1 will be equals to 0.1. So my k will be equals to 1 itself. K will be 1 itself. Okay, so my value of k is 1. Now, like we got the transfer function. So we got the transfer function. Transfer function equals to simply s by s square divided by 4 plus 0.6s plus 1. Okay, so this is my transfer function. Okay, this is my transfer function. So this is done. Now what about my like error? What about my error? So error simply is what error is simply minus 20 log of 2 zeta. Like if you want to remember the formula, you can remember, or you can derive from the basics. I have derived from the basics also. Okay, so error equals to minus 20 log of 2 zeta. So what is the error? So minus 20 log of so what is zeta? Zeta is 0.6. So 2 times 0.6 is 1.2. 1.2, which is equals to what? 1.2 log into 20. Okay, which is equals to minus 1.58 dBs. Okay, the asymptotic approximation of the log magnitude versus frequency plot of a minimum phase system. Basically, asymptotic approximation means the Bode plot they are talking about. So versus the log magnitude and the frequency plot, and this scale is in, remember, this scale is in decade scale. Scale is decade scale. Don't forget, decade scale. That's why this is straight line, right? That's why. Of a minimum phase system with real poles and 1 0 is shown in figure. So its transfer function will be, what will be its transfer function? So minimum phase system is, it is given that it is a minimum phase system, and we have to identify the transfer function from this by just seeing the Bode gain plot. Can you identify it? Now they have given you the options. Okay, they have given you the options. So from the options also you can understand few things. Okay, understand few things. So initially, like they are telling me, it is starting from minus 40 dB per decade. It is starting from minus 40 dB per decade. What does this means? This means I have two poles at the origin. At that instant, I got to know that I have two poles at the origin just by seeing here. So two poles at the origin, only C and D option are matching. So C and D option are matching. These can't happen. Okay, so these are automatically eliminated. Okay, now what next? After this, I have a like this becomes minus 60 dB per decade. From minus 40 dB per decade, this becomes minus 60 dB per decade at omega equals to 2. So obviously my slope reduces. That means I have pole slope reduces by 20 dB per decade. That means I have only a single pole at this 2 location. So here, yeah, this is also a single pole, and this is also single pole. That is fine. And this is also same. This is also same. This is also same. This is also same. So everything is same for these two. Only this coefficient, like that, this DC gain, like this is not even the DC gain. This is K. Value of K is change. Value of K is change. So for value of K, this hint is given. So we have to now use this hint. Okay, we just simply can't use this one. Simply can't use this one. Okay, so how to use this one? So what you can do is, I told you, right? I told you that like this is from the options itself. This is from the option itself. But first let's solve it from the basics. So then I will show you how to eliminate the options. Like I've already shown you the half portion I will show you next. Now the corner frequencies, what are the corner frequencies? Here, as I can observe, at omega equals 2 I have one pole. At omega equals to 5 I have 1 0, because it changes from minus 60 to minus 40. So slope gets added, so I have 1 0. Then at omega equals 25 again I have one pole. So I can write like the form of like standard time constant format, g of h of s, like this, k into, so first I have obviously two poles, that is for fixed. Two poles are fixed. That is one thing, because it starts from minus 40 dB per decade slope. Then at omega equals to 2 I have again one pole. So this is s by 2 plus 1. Then at omega equals to 5 I have 1 0. Then at omega equals to 25 I have another pole. Omega is 25 I have another pole. So here I have another pole. Okay, so these are the poles and zeros. These are the poles and zeros. So yeah, this is the thing. So now what you do is, so this is a standard form, and this is a form that is not given over here. This form is not given over here, so we can't do this. We can't do this. But first, let's find the value of k. How will we find the value of k? What you can do is, like, you have to find it. The magnitude at 0.1 is given 54 dBs. So here, what is the magnitude at 0.1? The magnitude at 0.1 is simply, we can ignore all this because the corner frequencies are much greater than 0.1. So this will become simply k by omega square, okay, or k by omega square, or equals to k by 0.1 whole square. Okay, so if this is k by 0.1 whole square, what does this become? So this is k into 10 square. Okay, now we have to convert this into log scale. You can either convert this into log scale, or you can convert that into absolute scale. So what we can do, it is given as 54 dBs. 54 dBs. Now if it is given as 54 dBs, so in absolute scale, what will be the value? 20 log of x equals to 54. Now my x will be simply 10 raised to power 2.7. This will be my x. Now what is 10 raised to power 2.7? Let me just find it out. Something 10 raised to power 2 power 7. Yeah, it's around 501. 501, or like approximate it as 500, because the answer will be something like this. So now what we do is, this value we put here. This value we put here. Okay, this is equals to x itself in absolute scale. So k equals to 0.1 square into 500. So it becomes 5. So k is equals to 5. Now 5 isn't even given in the options, because like this is not in the standard time constant format. We have to convert this into whatever this format is, simple format. So k is 5. So again we have to multiply by 5 everywhere, right? So multiply 5 in the numerator. No, like we have to just do one thing, just take, add this one up, right? Add this one up. So what I will do is, k is 5, that is fine. My g of h of s, k is fine, 5. This is s plus 5, add these two up by 5 divided by this is s square. This is s plus 2 divided by 2, and this is s plus 25 divided by 25. Okay, so this 5 cancels out, and this 2 into 25 goes above. So this becomes 50 into s plus 5, okay, divided by s square, s plus 2 into s plus 25. So this is my answer. So which option is matching? So basically g of h of s is this, and option, I think B, what was it? No, option D. Option D is matching. Option D is matching. So this is the question. So this is a GATE 2013 question, and here we have to find the Bode plot of a transfer function g of s is shown. Like the Bode plot is shown, and like they giving the gain in dB scale is 30 dBs at omega equals to 1 and minus 8 dBs at omega equals to 10 radian per second. The phase is negative for all omega, so it is like telling me minimum phase system only. And then g of s is what? The phase is negative for all when it's omega, means like there isn't any zero. There isn't any zero. Then we have to find the g of s. What is my g of s? Now, first thing what I observe, like if I observe from the question itself, that I am moving one decade from 1 to 10 times. I am moving one decade, and how much I am moving in the y-axis? How much dBs I am moving? I am moving 32 in minus it. So total I am moving 40 dBs. So I'm moving in one decade, I'm moving 40 dBs. So 40 dB per decade. So what happens when the initially the slope is 40 dB per decade? It means I have two poles, 20 times 2, so two poles at the origin. Two poles at the origin. So this option gets eliminated, this option gets eliminated. So only this and this option remain. Okay, this is this and this option can happen. This option and this option. Now out of this, which one is true? Now obviously, if this is 32 over here, this is in dB scale and this is an absolute scale. Obviously this 32 can't be here, so 39 will be my correct answer. So if you are in a hurry and stuff, so you can directly take this one and move on, or just you are just ending the exam, you can take this. Obviously we'll solve this in the proper method. We'll not do any assumptions and trick things. So how to solve this one? So here, how to find the value of k. How to find the value of k? So they have given the value of the gain at omega equals to 1. So you can use that, or you can use the slope method also. So obviously, let's do this first. So how to find the value of k? So they have given what we understand, the slope is minus 40 dB per decade. If you don't want to, if you didn't wasn't able to catch it, so let's do it manually. So what is my slope AB formula? Slope AB formula, it is here. My slope is A and B. Okay, slope AB equals to this, which is YB minus YA divided by log of omega B by omega A. Okay, so what is my A? A is 1 radian, B is 10 radian, and here what is my magnitude? 32, and here magnitude is minus 8. So minus 8 minus 32 divided by log of omega B by omega A. What is omega B? Omega B is 10. Omega, this is base 10. Base 10. So this becomes simply what? Minus 40 dB per decade. You can check, if you couldn't understand that how is it minus 40 dB per decade, this is minus 40 dB per decade. Now how to get the value of k? How to find the value of k? So how to find the value of k? So if you want to find the value of k, what you can do is that we can approximate our transfer function like this: g of s equals to k of s square. So if it is equals to k of s square, what does this mean? So this is k by, now at omega goes to 1, we have been given the value. Okay, so either what you can do, either you can calculate this in log scale or in simple scale. So magnitude will be g of j omega k by omega square. So in log scale, what does this mean? In log scale, (20 log k minus 20 log omega square. Now whenever omega equals to 1 is given, that means you're given 20 log k, because here we solve this question. If you want to remember that, well and good. If you don't want to remember that, don't need to remember that, totally fine. So here if you recall that what is it here. So always at omega equals to 1, you got 20 log k value. Whatever may be the square power, whatever may be the power, the cube square, whatever the power, omega equals to 1, you always got 20 log k. So you can directly equate that. If you're fast enough, obviously you can directly equate that. If you're slow, you need to go step by step. Now we are slow, obviously, that's why slowly learning right now, so that's why we're going slow. When we'll solve questions, we'll go very fast. So this is 20 log omega square. So this is 20 log omega square. This becomes like omega at omega goes to 1. I am getting 54 dB, and this is 20 log base 10, and this is minus 0. So K is simply equals to 10 raised to power 2.7. Okay, and okay, this is 54. Sorry, this is 30. Sorry. This is 32. Sorry. 54 was the previous question. It is 1.6. So let me just do this. 10 raised to power 1.6. It is 39.82 almost, or 81 you can say. So this is the answer basically. So here like you can write that 39.8. So this is correct, and this is also not correct. So this is correct. Like from here you can find out, or if you don't want to find out from here, what you can do is like it's just the same thing only. What you can do is like simply you convert this one into absolute scale. Okay, 32 into absolute scale. So you convert this 32 dB into absolute scale. So this is 10 raised to power 1.6. Now you equate this one with K by 1 square. Okay, because at omega goes to 1 you know the value. Okay, or if you want to find the value of K from here also you can find that. You convert this into absolute scale. So this one minus 8 dB into absolute scale. So this is 10 raised to power minus 0.4. So like 8 divided by 20 minus 0.4, and you equate this one with K by 10 square because omega is 10 right now. So now you get the value of K. So you will get the same. I'm just cross verifying. Into 100. So you get the same value, 39.81 itself. From here also you get the same value, K equals to 39.81. So whatever you do, that's what the first step was telling me, that if the gain at any frequency is given, you just equate that approximate transfer function at the frequency and gain from that part. Okay, simple only. So this is what the first thing is giving. Now with respect to omega axis, what do you mean if the intersection of the line is with respect to omega axis? This will understand in the next question. So this was a gate question, good question. And here, okay, just hold on a second. Yeah, we have the another question. So this is also a gate question. I don't remember like which. Yeah, this is 2014. Just written. This is 2014. So gate. I don't remember if this E or something. So this is 2014. Okay. Now, if the Bode magnitude plot of the transfer function is given like this, you have to find A by BK. All these unknowns you have to find. So for you to find these unknowns, you can't use any tricks or shortcuts because this time NAD has come up. So you can't eliminate options. You have to go by the basics now. So how to solve this by the basics? First thing is you mark this is giving in octave. So you convert this into decade scale, or you can use this octave scale also. Why? Because here multiple of 2s are given. So sometimes octave scale is also useful. We'll understand that is using the octave scale helpful or the decade scale. So here this 2 4. So basically they have also given the conversion. So they have given you everything basically. So let's start by understanding the slope differences. So these are the slope differences here. So let's understand the counter frequencies. So here I have one counter frequency. How much slope is changing? 6 dB per octave or plus 20 dB per octave. So obviously I have a 0 at this frequency. So first let me write the standard time constant format. K I will have. Okay, here also I'm saying that it is starting from what? It is starting from a like minus 6 dB per octave, the slope. So minus 20 dB per octave, 20 dB per decade. That means I have a single pole at the origin. So I have single pole at the origin. I have single pole. Okay. I have single pole at the origin. Then obviously I have a 0 at omega equals to 2. So 0 Then what else I have? Then slope increases again. So I have another 0 at omega goes to 4. So I have another 0 at omega. So here also you can understand that they have given you a few things. So you have 2 zeros and 3 poles from 4 poles. You can understand from here itself. But still, let's not use that. Let's use our basic things. So I have another 0 at omega equals to 4. Then after this, at omega equals to 8, I have a pole because the slope is reducing from plus 20 dB per decade to 0 dB per decade, or plus 6 dB per octave to 0 dB per octave. So I have a pole at omega equals to 8. After that, what is happening? After that, this is again further reducing. So at omega equals to 24, what is happening? My slope is becoming minus 6 dB per decade. So again I have pole at omega equals to 24. Next, again I have another pole at omega equals to minus 12. Another pole at omega equals to minus 12. Sorry, minus 36. Because here the slope is further reducing to minus 12 dB per octave. Okay, so it is ending at minus 12 dB per octave. That means the number of poles will be how much? Number of zeros minus number of poles should be equals to 2. Here number of zeros is 2, number of poles is 4, so total 2. Yeah, that is fine. This is correct. Now let's see this. So they have given you this location. This is what? S by 2. So omega equals to 2 is given. This is given, but this is not given. S by 4 is not given. Here this is A times S. So A equals to 1 by 4. Just remember that A is equals to 1 by 4, not 4. A is not 4. If this was given as S by A, then you could have written A equals to 4. So don't get confused by this. So A will be equals to 1 by 4. A will be equals to 1 by 4. Next, this 1 by 8 is given, fine. This 0 pole is also given. This B is not given. 36 is given here, but this 24 isn't given. So my B is equals to 1 by 24, not 24. So B is equals to 1 by 24. That is fine. Okay, all these things are fine. Okay. So yeah, this is fine. Now you have to find A by B into K. Now K we don't know. K we don't know. Obviously we can't put S equals to 0. That is difficult. But what we can do is, like this thing is that if we put the intersection of this line is 8 over here. The intersection of this line is 8 over here. So this is what we need to find. So how to find this one? So if you remember the formula, what was my formula? Like for K, formula for K was omega, formula for omega GC. Omega GC was K raised to power 1 by N, where N was the number of poles at the origin. Okay, if you remember, like when I had poles at the origin or something. So it, like, because all these things will be ignored, I'm talking about only this part. Okay, if let's say if the Bode plot for only this one is given, Bode plot for only this one is given. Omega. This was my omega GC, and this is my what? K by S. Here my slope is minus 20 dB per decade. Okay, if you remember the formula, okay, well and good. If you don't remember the formula, we can solve this simply. So this is my omega GC here. So like what we are doing is we're assuming, like, that's why they have given this to find the value of K. So this and these are same. Okay, K value will start from here itself, right? K won't change for this line and this line. Like for this line and this line, the value of K won't change. So I will approximate my K from here instead of this, because finding K from here is difficult for me. So obviously I will approximate my K from here. So that's why I use this formula. Okay, if you don't want to use this formula, what you can do? You can simply use this thing, that like this is the formula. If you don't remember this formula, then simply use this. That what is the magnitude expression of this one? So let me name this as G dash of S. So G H dash of J omega equals to K of omega. Now let me convert this into log format, or what you can do is, what is a unity gain frequency? It is basically where the gain is 1 equals to 1, where this equals to 1, so K will be equals to omega itself. If this was, let's say, square, so this will be omega square. So whatever you choose, so K is omega, and omega is given, omega GC is given, it is 8 radian per second. So our value of K will be 8. Okay, from here if you want to understand, from here if you want to understand, whatever you try to understand, that is well. So I would always recommend like mugging up the formula. You can do it from the concept itself. Okay, or what you can do, what else can you do? In dB scale, we can convert this into dB scale also. Basically taking the same thing only, log base 10K minus log 20 log base 10K omega equals to 0, because log base 10 1 is 0 always. So unity gain frequency is log is 0. So my this obviously, like from here also you can understand that, yeah, this is K equals to omega itself. Okay, so K equals to omega itself. Like if you want to do it in log scale, if you want to do it in omega scale, whatever scale you want to do, you can do. So here K is 8. Okay, K is omega. So K value we found out is 8. K value we found out is 8. So I hope you understand the K value for this graph, what they have given. They also want you to use this information because anything else isn't given. So only you can find the value of K from this information itself. So K value for this graph and for this graph are same because they're starting from the same point and the slopes are same. That is why, that is the reason. Okay, so K for this graph and this graph is same. Okay, you don't have to worry because you are basically approximating it. So now we have to find the value of A by B into K. So A is 1 by 4. So what is A by B into K? So A is 1 by 4, B is 1 by 24, and K is 8. K is 8. So this becomes 3 by 4. So this becomes 0.75. Okay, so yeah, this is the answer. Basically the answer is this one. So this is what I meant by finding the value of K from the intersection of omega axis. This is what I meant here. Put the value of omega in the approximate transformation and equate it with 1 you can do, unity value of frequency you can do. Okay, put the value of omega, that also I meant. Okay, so simply that is what we did. Put the value of omega, we simply put the value of omega here, right? Put the value of omega and we found out value of K. Okay, that is what I meant. So let's do another question. So this is again another gate question. I am forgetting to write the years. Okay, this is another gate question, but this is I think 2016 IC Bangalore. Okay, so again, right, they have given you the Bode plot and you have to which one is the best approximated transformation basically for this given Bode plot. Now can we eliminate anything from the options? Again this time the dB scale or decade scale is given. Okay, so here what we observe is like we have the slope changes here, so they haven't given information about the corner frequency. Here also they haven't given information about the corner frequency, so don't get confused by this. These are not my corner frequencies. Okay, this is just they have given some information that at this point my magnitude is 0 dBs or my magnitude is 1 in absolute scale or decimal scale. So these are the information. 8 and 0.5 are not my corner frequencies. Just be careful about that. But what other option can I get is that I have a 0 initially. At s equals 0. So yeah, all of these, these three have s equals 0 at s equals 0, but this doesn't have. So this one gets eliminated. Okay, this one gets eliminated. Next, here I have minus 40 dB per decade. So I have two poles at some location, which I don't know right now. Okay, so this also gets eliminated because here at some corner frequency I have two poles. This for sure because this is 0 dB per decade because here there is no slope change, but suddenly it becomes minus 5 dB per decade. So that means I have 2 poles at that location. So I have 2 poles at this location, but this is telling me that I have 1 pole at one of the counter frequencies. Like all of the counter frequencies, I have only 1 pole. That is not possible. Here I am seeing the slope changes 0 dB, like from plus 20 to 0 dBs. That means I have 1 pole here and I have 2 poles here. That means this is wrong. This is wrong, because it is telling I will have always 1 pole at each counter frequency. No, here I have 2 poles at a counter frequency. So this is wrong. Only these 2 are correct. Like, I mean, these 2 can be my possible answers. Now, is this the answer? Let's check for the answer. Okay, so like this one also can't be the answer. Why this one can't be the answer? Because what this is telling me is that I have a counter frequency at omega equals to 0.25. Like this is the tau. 4 is the time constant. So 1 by tau is 0.25. This is telling me that I have a counter frequency at 0.25. Can I have a counter frequency at 0.25? This is always constant. Like slope is constant. Okay, slope is constant here. Slope isn't changing. So obviously this one is eliminated. Only option A is correct. Okay, from the option itself you can directly eliminate. Obviously now we'll solve this using the fair method. Okay, so how to solve this using the fair method? So let me first draw the this plot basically. So exam hall you can use that trick, but if you want to solve this fairly in your home, obviously you will use this one. Magnitude G of J omega n dBs. So plot we have been given something like this. And here we have 0.5 and here we have 8. Okay, and this is 0 dB. This is 0 dBs. One more information is given: the magnitude at this point. The magnitude at the corner frequency is given. The slope at the corner frequency, the corner frequency isn't given, but the magnitude at the corner frequency we know. So magnitude at the corner frequency is 12 dBs. Now, as one thing I'm observing, this is in multiples of 6. So whenever the magnitude is in multiple of 6, what I can do is I can convert this into octave scale. This is not mandatory, you don't need to do this, but as my magnitude is in the multiple of 6, I will do this. In simple decade scale also you will do this. Okay, we'll solve using both scales, but first I will solve it using the octave scale. So here I will convert this 20 dB per decade to octave scale, as I am observing that my magnitude is multiple of 6. So this becomes 6 dB per octave, and this becomes minus 12 dB per octave. Okay, so what can I say is that one thing very interesting fact, as I told you, right, multiple of 6. So what is the interesting fact here? As I move one octave, this will move up by 6 dBs. As I move another octave, this will move another by 6 dBs. So I'm observing, like here this is 12. Okay, that means I move total by from 0 to 12. 12 dBs I move. So if I move 12 dBs, how many octaves did I move? I move 2, because the slope is constant here. Slope is constant until here. So I move 2 octaves. So that is why I was converting it into octave scale. So this is let's say this is 1. So obviously octave means 2 times the previous frequency. So this will move here, the magnitude will become 6. Another octave I moved, the magnitude will become 12. Very simple. Now here what is happening? I am moving, like the slope is here minus 12 dB per octave, and from 12 dBs, like the magnitude still here is constant, from 12 dBs I'm going to 0. So total I'm moving 12 dBs, and the slope is minus 12 dB per octave. So if I move by 12 dBs, that means it is moving to 0 dBs. Like in 1 octave I'm moving 12 dBs down. So in 1 octave I'm moving 12 dBs down. From 12 dB I'm going to 0. Yes, and this is also telling me that my slope is minus 12 dB per decade. So what is this distance? This distance is 1 octave. This distance is 1 octave. So if this distance is 1 octave, obviously here whatever the value will be there, this will be multiplied by 2. So this is 8, so this will be 4. So 4 times 2 is 8. So the slope here is minus 12 dB per octave. So if I move 1 octave, I should move down by 12 dBs. Is it happening? Yes. My magnitude is 12 here, and moving down by 12 dBs, magnitude becomes 0 at the 8 frequency as I move 1 octave. So obviously this is 12 dBs. So yeah, this is minus 12 dB per octave. Yeah, that is fine. So I got my corner frequencies from here. 2 and 4 are my corner frequencies. And value of k. What about the value of k? So for value of k, what you can do is, again you can use this. Again you can use this. Simply, like I'm doing the shortcut here. Okay. K by omega, like as I have a 1 0. So this time this is not by omega, this is k times omega, should be omega gc should be equals to 1, because at this frequency my magnitude is 0 dBs, or in a decimal scale 1. So what is omega gc is 0.5. Omega gc is 0.5. Okay. So k will be equals to 2. So don't get confused, like you equate this with this here. No, this is some other like value. This is going to, again magnitude is going again to 1, but this is a starting magnitude, right? That's why we equate with this one. Don't equate with 8. Don't equate with 8. Just be careful about the initial slope. The initial slope always gives me information about the k. Just remember, initial values, right? This doesn't give me information about the k. So k I got the corner frequency. Let's just write it in the standard time constant format. So g of h of s equals to 2 times, I have a 0, and after this I have only poles I have. So one pole I have at s equals to 2, so s by 2 plus 1, and another pole I have at s equals to 4. It's equals to 4, I have another. Okay. So yeah, this is basically my transfer function. So you can equate it here. Okay, sorry, I have 2 poles here. Sorry, I have 2 poles because the slope is minus 40 dB per decade. So yeah, this is, you can equate this one. You're getting the correct answer. Now, should you do this in decade scale? Yes, you can. Obviously, you can do this in decade scale also. So like this was in octave scale. In decade scale, what do you do? Simply you do one thing, that you know the slope here, so you mark these points as A and B. Okay, you mark this point as AB. Now again use the simple slope formula, like that is what I did here. You use the slope formula without writing it, because sometimes you don't need to write it, you can solve it just by seeing the graph. Okay, that is what I am trying to teach you. Just by seeing the graph, how can you find the corner frequency, all those things. Don't have to write anything, so that it saves time in other difficult questions. That is more important. Bode plot is very simple topic, so you have to save time here. Okay, so here this becomes slope AB equals to this YB. What is YB? YB is 12 dBs. So 12 minus 0 by log base 10 of omega B. I don't know the first corner frequency, this is, and omega this is 0.5, and this is what? This is 12. Sorry, this is 20. So 20 by 2. This is wait a second. Omega P1 by 0.5. with log base 10 equals to 12 by 20. So this is 0.6. So omega p1 by 0.5 equals to 10 raised to power 0.6. Simple, I'm converting into log format. So this is 10 raised to power 0.6. What is 10 raised to power 0.6? If you remember correctly, it is simply 4, because just remember one thing, that 10 raised to power 0.3 is almost equal to 2. This you have to remember. Okay, anyhow you have to remember this, please. Okay, I'm begging you guys that you have to remember this. 10 raised to power 0.3 is 2. Now if you simply square this one, you will get 4. Square this one and this will become what? Multiplied by 2. This is 2 square, so this will become 4. So omega p1 will be equals to 0.5 into 4, which is equals to 2 itself. Okay, 2 radian per second. And the same thing you do, same thing you apply here. So let me name this. Like this is the slower process that I'm talking about. So C and D. Okay, C and D. We solved this using 3 methods. Basically, first the optional elimination, second is the octave scale, and third is the decade scale. So now again you write the slope basically. So now the slope is minus 40 dB per decade. So it is starting from like ending to 0 dBs and starting from 12. So 0 minus 12 divided by log of 10. Starting from that, so omega p2 will be here and ending to 8. Okay, and the slope here is minus 40. So yeah, slope here is minus 40. So this is minus 12 by omega p2. So here it becomes log of 10 8 by omega p2. Am I doing something wrong? Plus 20 is going to 0. Yeah, 8 minus correct minus 40 is correct. So this becomes 2 by 5 itself, isn't it? No, this becomes 3 by 5. 4, no, 4, sorry, this becomes 3 by 10. Yeah, 3 by 10. This becomes 3 by 10 basically. 4 times 3 into 4 times 10. 3 by 10. Now this is omega p2 is equals to simply 8 by omega p2 is 10 raised to power 0.3. Again, I told you to remember 10 raised to power 0.3 is 2 itself. So omega p2 will be 8 by 2. Okay, now this is how you can identify the corner frequencies. Whatever like method you find suitable, use that method. Okay, so yeah, this was basically it for this question. So this is the most important lecture. Do try to repeat the lecture if you couldn't understand anything, because from here the main questions will come and you can do the questions in seconds. As I told you, right, you can just eliminate the options, or you can just use few formulas. If you don't want to use the formulas, don't need to use the formulas. You can directly equate this one. Don't need to use formulas. You can directly equate in the with the magnitude function itself, and the corner frequency you can easily identify, right? So all these things, have you got the idea how to convert into octave scale, how to convert into decade scale, all those things. So the most important lecture. And obviously remember few things, right? 10 raised to power 0.3 is 2, 10 raised to power 0.6 will be 4, because it is simply the square of that one. So yeah, this is it for this lecture, and I will see you in the next lecture with error in Bode plots and Bode plots for second order systems. So yeah, thank you for watching. So what is the next question telling us? The Nyquist plot of the OLTF is given, and the Nyquist plot is okay. Nyquist plot is not given. It has told that it does not encircle the critical point minus 1, 0. The Nyquist plot of this OLTF does not encircle the critical point minus 1, 0. Okay, of the obviously g of h of s plane. It has not mentioned here, but we will assume it is talking about the GS h of s plane when k is equals to 10. So when k is equals to 10, it has told that it does not encircle the minus 1, 0 point, but does encircle the critical point minus 1, 0 once when k is 100. So when k becomes 100, it encircles that critical point. When k is 10, it does not encircle the critical point. Then the closed loop system, it is talking about the stability, right, for different values of k. So what you can do, there are two methods to this. So now we obviously will use that Routh method also and this method also. So method one is simple Nyquist plot, right? Nyquist plot. So basically what first thing what we know, we have been given the OLTF, and from the OLTF can you get any information? If you have been given the OLTF, always find the number of poles on the right hand side of the OLTF. Okay, OLTF. So are there any poles on the right hand side? This is on the left hand side pole. And what is this? This is like, just use that Sridhar Acharya formula, or simply directly from the Routh criteria, you can see that all coefficients are positive, so there are no poles on the right hand side. So this has 0, this also 0. Okay, hence I can directly say P plus OL equals to 0, or what you can say is, like, what you can do is find the roots of the second order equation. Okay, and you will find out that this is coming to be on the negative side of the exponent, right? Roots are on the negative side of the exponent, so roots are on the negative side of the exponent. So from OLTF, my P plus OL equals to 0, which is simply equals to same as P plus 1 plus OL. Now this has got installed into your main IO. So this is, which is same as this, right? Same as this. So now this is this, right? Now what I will recommend is, we have to find the number of encirclements around the minus 1,0 point. So for k equals to 10, it has told it is 0. So now we'll decode the other information. For k equals to 10, my n minus 1,0 is 0, right? Okay, and like I will do this now. I will find the stability for this one. So what is my formula again? That formula, this is 1 n minus 1,0 equals to p plus 1 plus OL minus z plus 1 plus OL, and p plus, this is 0, right? This is 0, and this is also 0. Hence my z plus 1 plus OL equals to 0. Hence I don't have any closed loop poles on the right hand side of my S plane. So this system is stable. System is stable. Closed loop poles are on the, so system is stable basically. Left hand side, so system is stable. Okay, system is stable. Now what about when k is 100? So when k is 100, it is telling us that it is encircling the critical point. Okay, the direction it hasn't told us, so that is an issue. So if they should have told us the direction, right? If they haven't told us the direction, if we are getting the value of z as negative, we'll assume other direction. So what I will assume is, this is encircling in the anti-clockwise direction, right? Anti-clockwise, the positive direction basically. Okay, if I get a negative value, right, of z, then I will change my direction. Okay, so sometimes it may happen they don't give the direction, then you have to assume the direction, right? Although in this question they should have given the direction. Assume clockwise direction of Nyquist contour and anti-clockwise direction of the encirclement basically. Of the encirclement, right? In the anti-clockwise direction of the encirclement. So yeah, that is what we assume. Now here it is given 1, right? It is encircling, but does encircle the critical point once. Okay, 1 k is equals to 100. So K is 100. I assume it is anti-clockwise, so it is 1. So my P, that is same, right? P plus this is same, this doesn't change, right? So just hold on a second. Yeah, sorry for the interruption again, like one call came up. So my n is minus 1 comma 0, right? N is minus 1 comma 0 equals to 1, okay, in the anti-clockwise direction, I'm assuming. Okay, now if I put this in the equation, n equals to this 0 minus z, so my z plus is coming negative, which is not possible, right? Negative, not possible. Negative, not possible. Okay, like z plus is coming out to be minus 1, right? To minus 1. Okay, so what we'll do, we'll assume different direction of contour. So this contour is not correct. Assumption of contour was not correct, or whatever you might say. Like assumption of contour may be correct, but if the question has told us that it is encircling in the clockwise direction, then also it is correct. But I have to assume some convention. So what I will do is, I should have written it down in the question. While making the question, I made a mistake. I should have written it down that once in the anti-clockwise direction. I should have written it down. So at least one thing should be given, right? Anti-clockwise direction, or the Nyquist plot should be given. So that's my bad. Okay, maybe I written it down, then again I deleted it. Okay, so yeah, the question is anti-clockwise direction, then this question will be better. So now this is getting wrong, so what I will write is, my assumption for Nyquist was wrong. Okay, then what is my assumption? Then what I will say is that this is anti-clockwise. Okay, this is anti-clockwise. Now this is anti-clockwise, then my n minus 1 comma 0 is minus 1, because I'm expecting a clockwise encirclement, right? Opposite direction of encirclement. So n is minus 1, and this is anti-clockwise, right? Anti-clockwise encirclement. They have given us in the question anti-clockwise encirclement. So if n is minus 1, now what you do? So basically you do, right? So now you put in the formula, minus 1 equals to 0 minus z plus 1 plus OL. Okay, so my z plus will be 1. So I will have one right hand pole of one right hand closed loop pole, right? One right hand side closed loophole, basically one right hand side closed loophole, right? So I will have one right hand side closed loophole. So what is the question telling? Yeah, it is unstable basically. So when k is 100, it is unstable. So you could have done it very fast. Okay, I'm just explaining everything to you, that's why I'm doing it very slow. Just it will take 1 minute, right? So for k equals to 100, this is unstable, and for k equals to 10, this is stable. So option B is correct. Okay, oh, all of them are option A. Okay, I have to change this. B. No, this is not C. Okay, so this is about the this method. Now can we solve this using any other method? Yes, we can, right? How we can solve this any other method? Basically you can use the Routh-Hurwitz criterion. So here I will tell you how to use the other method also. If you are confused in Nyquist, or sometimes it's easier to solve in Routh-Hurwitz instead of Nyquist, right? So then we'll solve it using Routh-Hurwitz, because Nyquist problems can be solved using Routh-Hurwitz also. Okay, because they both of them tell us the absolute stability. Sometimes it is easier for us to solve with Nyquist, sometimes it is easier for us to solve with Routh-Hurwitz. You have to choose which one. That only you will get understand, that only you will understand when you solve multiple questions, right? Multiple questions, that only you will understand when to use what method, right? So Method 2, Routh-Hurwitz criteria. Okay, so Routh-Hurwitz criteria. So what you do, we have been like whenever OLTV is given, you can use two methods. Whenever OLTV is given, you can use two methods, right? As I told in my that previous bisection also, that how to solve Nyquist problem. So here I'm basically doing the application of that. So we'll copy the OLTF, okay, and we have to talk about the closed loop stability. So what I will find the closed loop characteristic equation, and from there I will find the about the root side, whether the roots are lying on the right hand side or the left hand side. So this is my g of h of s, right? Now what is my 1 plus g of h of s? Simply 1 plus g of h of s equals to k divided by s square plus 2s into s plus 1. Okay, this is 1 plus g of s, so this should be equals to 0. So like my equation becomes, this is s cube plus 2s square plus 3s plus s square plus 2s plus 3 plus k. Okay, so now let me like rewrite everything, right? Sort everything out. This is s cube, and this is simply plus 3s square, right? 3s square plus 5s plus 3 plus k. Okay, did I have any k with? No, I don't. So basically this is s cube plus 3s square plus 5s plus 3 plus k equals to 0. Okay, this is what my characteristic equation is, and from here this is basically telling me about the poles of the closed loop poles, basically closed loop system, right? So now we can use a shortcut. What is shortcut? That internal product should be greater than external product for what? For system stability. So what do? You basically make internal product. What is internal product? 3 times 5, right? Should be greater than external product, that is 1 times 3 plus k. 1 times 3 plus k. Okay, so my k from this inequality should be less than 12 for stability. Okay, now you just check the options, right? You just check the options, like where my k is less than 12 and it is stable, and if my k is greater than 12 it is unstable, if my k is equals to 12 it is marginally stable. So good derivation of Routh, right? So like here I can see obviously k is less than 12, this is stable. If k is greater than 12, this is unstable. Only this option will suffice, other options will not be eligible for this, right? Will not be incorrect, they will be. So this was the question 21st. Now let's go to the next question. So next question is telling us that we have a unity feedback control system characterized by the following open loop transfer function. The OLTV is given, so whenever OLTV is given, you can do it obviously with Routh, but you have to understand that whether doing it with the Routh will help you in solving it faster, or it may take more time. That only will come with experience when you solve each question, right? When you solve each question. So Nyquist contour is given, OLTV is given. Okay, this contour, this plot, Nyquist plot is also given. Now it is telling us that my k is 0 to 1. So k, right? K is the system parameter. K is varying 0 to 1, and k is also here given, right? K is also given here. Okay, so this question has made us easier that it has given k over here. Okay, if k wasn't given, something else was given, 10k or something, then this question would have been again become trickier. Okay, but as simple k is given, then which is very simple. K is varying from 0 to 1. Now if k is varying from 0 to 1, what does this mean? At k equals to 1, what does this point become? This point becomes the critical point. And if it varies from 0 to 1, what does that mean? So if let's say this is my minus 1 point. If this is my minus 1 point, k is varying from 0 to 1, so it never touches my minus 1 point, so it never touches my critical point, so there aren't any encirclement around the critical point. Okay, that is one point to note here. Also here what I can observe, is the OLTF stable or not? Is the OLTF stable or not? Like whenever you're trying to solve the Nyquist, right, always check if the OLTF is stable or not. OLTF is stable. If you said yes, then you skipped a bit. Why? Because you might have just assumed that this is a second order equation. This is a square plus 3 square, 3s plus 10. But this isn't second order, right? This is what, third order, and there is coefficient of s missing. So whenever there is a coefficient missing, obviously the system will be not stable. Like the open loop transformation won't be stable. Okay, that we know. Open OLTF won't be stable. So obviously we have some poles lying on the right hand side, right? So this you can solve using three methods. Only with the Nyquist, both with the Nyquist and Routh, and only with the Routh. So we'll see all the three methods. So first method is with the Nyquist itself, right? Method 1. The Nyquist plot only. So if you want to solve it with the Nyquist plot only, how we'll solve it? So this is the Nyquist plot. Okay, I've just drawn it same ditto, okay, as it is given over there. Now what are the informations given to us? One of the information is given to us is that, like, what we can find is, we don't know about like how many poles are there on the right hand side of the spline, right, of the OLTF. If we don't know about that, then we won't be able to comment about the right hand side poles of the closed loop transfer function. Okay, we have to know about the right hand side poles of the open loop transfer function. From there, what we'll do, we'll find the we'll put that in the that minus 1 comma 0 encirclement equation, and from there we'll get our solution, right? But hence we have to find P plus OL, right? P plus OL. How to find that basically? So what you can do is, basically how to find that, we use the first equation, right? What was the first equation? It was the n 0 comma 0 encirclement around the origin, which is equals to P plus OL minus Z plus OL basically. Okay, so it is P plus OL minus Z plus OL. So now how many encirclements do I have? I have, around the origin I have one encirclement, right, and two encirclements. Okay, like you can use that method also, where we put a straight line. Okay, but sometimes where you will get stuck is like questions like this, right? Here you will get stuck. Okay, here you will get stuck if you want to use that method. So let's say this is my critical point, and if you want to use a straight line, so you will get confused. So if you get confused, don't use this method, just use the simple encirclement method that I was talking, right? Just swiping the red pen and just checking how many encirclements are there. Don't use this method. For the people who want to use this method, how to use this method to find the number of encirclements? What do? You from the critical point, you draw a straight line and cut the contour. Okay, now if you cut the contour here, what do you see? You see one in the anti-clockwise and one in the clockwise, so it cancels out, it becomes 0. Now you might say, sir, you can also take this straight line here, straight line here. So if I take this straight line here, what happens? Okay, let me just take this straight line here. What happens? One is in the anti-clockwise, one is in the clockwise. Okay, and also there is another cut. There are two cuts here. So if there are two cuts here, they cancel each other out of the same plot, right? So what is this cut telling us? This is in the clockwise telling us, this is in the anti-clockwise telling us. Okay, that's why they both of them cancel each other out, and we're only left with these two. Okay, that's why. So if this is confusing to you, don't use this method. Don't use this. Only use the simple method. What is the simple method? This, let's say this is the critical point. One is the like encirclement around that critical point in the anti-clockwise direction, and there is another encirclement in the clockwise direction. Sorry, not in the anti-clockwise, in the clockwise direction. Okay, there aren't any encirclements around the critical point of other two contours, right? Okay, use this method if you get confused by the previous method, right? So yeah, this was basically the brief summary, because I told you that method, right, in the previous. That's why, like, I thought, yeah, it may become a bit difficult for you to solve using that method only. So I told you the two methods here, right? So now let's come back to our question. So here, what is my n0, 0? N0, 0, I can see one in the anti-clockwise direction and another one in the anti-clockwise direction. So two in the anti-clockwise direction. So I have two in the anti-clockwise direction. And what is P plus OL. What is P plus OL? P plus OL, right, is what I have to find basically. P plus OL is what I have to find basically. And what is Z plus OL? What is Z plus OL? So Z plus OL is number of zeros on the right hand side. How many number of zeros are on the right hand side of the OLTF? None, right? None. It is only s equals to minus 2 is one of the 0 and it is on the left hand side. So ZOL plus is 0. So we have been given the information about ZOL plus, and from there we have to find the POL plus, and from there we'll find the Z1 plus OL plus. So it is like circling around, right? So this is so this is not minus 2, sorry, this is 0, because we have zeros around on the right hand side of this plane. So this is 0. So my POL plus, I have 2 poles on the right hand side of this plane. Obviously you can solve it using the Routh, right, and get your sign sheets, and that will do in the next method basically. So yeah, that is what this is. Now you put this equation in the second equation, right? Like you put the value of P plus OL in the second equation. So this is equals to simply P plus 1 plus OL. So now I will use the second method basically. N minus 1 comma 0 equals to this P plus 1 plus OL minus Z plus 1 plus OL. Okay, so if I use this one, right, now what is my encirclement around the this minus 1 point? So what I told, right, if I'll just copy this contour, right, and if I, let's say I draw a asymptote of which real part is minus 1 comma 0, right, minus 1 comma 0. Minus 1 comma 0, right, whose asymptote is minus 1 comma 0. If its asymptote is minus 1 comma 0, then what does that mean basically? So my k is varying from 0 to 1, so it will never touch the asymptote. So I can, like, how many encirclements I will always have around the minus 1 comma 0, I will always have, like, this will never reach this point. So I can exactly find the encirclements here. This will never reach this point. Okay, as this will never reach this point, my all these plots will never reach this point. So how many encirclements will I have around the this minus 1 comma 0 point? This plots will never reach this point. So how many encirclements? 0, because I have nothing here. I have nothing here, right? No plots are reaching this point. This is my minus 1 comma 0 points, as k is varying from 0 to 1, right? K is varying from 0 to 1. It will never reach this point, hence I will not have any plots here. Okay, and I will not have any encirclements. All are lying around here in this region. Okay, I have nothing here, so it is 0. So n minus 1 comma 0 is 0. Okay, now what is P plus 1 plus OL? That already I found out, and this is minus Z plus. Okay, so yeah, this is one more thing, and obviously, right, this is in the anti-clockwise direction. That's why I wrote it plus 2. Why? Because my contour was in the clockwise direction, hence my encirclement is in the anti-clockwise direction, and I took it as positive. Okay, that is one thing. This is Z plus, and Z plus equals to 2. Z plus equals to 2, right? So Z plus is equals to 2 itself. So it is not simple. Z plus is 1 plus OL. So I have two closed loop poles on the right hand side of my S plane. Okay, so by this you can directly tick mark that my answer will be 2, right? This is talking about the number of poles of the closed loop transfer function that lie in the right half of the S plane basically. So this is 2. This is 2. So now let's go for the method 2, which is a mixture of both Nyquist and Routh. Okay, so if someone doesn't know about the concept of that encirclement on the origin, what they will do is they will find the number of poles, okay, on the right hand side of the S plane of the G of HFS transfer function of the OLTF with the help of Routh. Okay, so method 2. Both Nyquist and Routh. Okay, both Nyquist and Routh. So like we have to find the POL plus. Okay, P plus OL. So we'll find POL plus with Routh-Hurwitz, right? How to do that? I will write G of H of S. What is my G of H of S, right? G of S H of S equals to 10k S plus 2 S cube plus 3s square plus 10, right? Plus 10. So this is this one. Now what we do? We write the Routh table. For this, to find the poles, right? We have to write this in Routh table, right? Standard Routh table. So obviously we have a coefficient missing basically. So this is 3s square uh, plus 0 times s plus 10 equals to 0. So we'll write this in Routh table. Okay, here I have s cube, here I have s square, here I have s to the power 1, here I have s to the power 0. Okay, so what is this? S cube is basically 1, s to the, this is 0, this is 3, and this is 10. So what you will do is, this will be minus 10 by 3. Okay, and this is 0 itself. Okay, so I'm doing this directly, not explaining anything. Okay, and what is this? Am I doing this correctly? This was s square, right? Yeah, s cube s square, yeah. And this will be simply, this will come directly over here, right? You remember, right? We studied it out. So this will directly come over here. This is 10 and this is 0 itself. So how many sign changes I have? I have plus, plus, minus, plus. So I have what? Here one sign change and here one sign change, right? Sign change. Okay, so I have two sign changes, basically two sign changes. So if I have two sign changes, what does that mean? That means basically that I have two right hand poles, right? Hence two right hand poles, basically I have two right hand poles, right? So if I have two right hand poles, what does that mean? Now I will simply put that in the same equation, right? Put in the same equation. Okay, and I will find the solution. This is this. Now I will find the solution, right? Simply copy paste, right? So like this method is copied itself, right? So yeah, after this obviously I will use this like same method only. Obviously that's why I told it that we'll use both Nyquist and Routh. Now if you only want to use Routh, okay, you don't use this because like if someone wants to use this, they can use this. Now if you only wants to use, someone only wants to use Routh, right? So if someone only wants to use Routh, method 3, Routh-Hurwitz criteria. Okay, if someone only wants to use Routh, what they can do is, like this is one, like I will write the characteristic equation. So 1 plus g of h of s, which is k into s plus 2 basically. Okay, and we have what? S cube plus 3 square plus 10 equals to 0. So basically this becomes s cube plus 3s square plus 10 plus k into s plus 2 equals to 0. Ks plus 10, not this, 10 plus 2k basically. So like we can obviously find the condition value of k for which the system will remain stable or unstable. That simply we can find it with internal product and external product. So for stability, my internal product should be greater than external product, right? So my internal product is greater than the external product. What does that mean? So that means greater than this 10 plus 2k, right? So if this is greater than this 10 plus 2k, and hence k is greater than 10. So for k greater than 10, system will be stable, but the range given is between 0 to 1. Okay, the range given is between 0 to 1. K is never going to 10, never going greater than 10, so it will always be unstable. So definitely there will be some poles on the right hand side of my S plane, so these options will be there. This option is eliminated. So how many, that we have to found with the Routh array table, right? So always unstable. Okay, always unstable. So now basically now you just write this in the Routh table. So let me make the Routh table. S square s to the power 1, s to the power 0, right? S to the power 0. Okay, now what you write, this coefficient 1k, okay, 1k, and this one is 3 10 plus 2k, 3 10 plus 2k, 3 10 plus 2k, right? So now you write this. So now basically solving, this becomes k minus 10 plus 2k divided by 3 itself, and here it is 0, so this will directly come down here, right? This will directly come down here. This is 10 plus 2k. Now if my k is varying, okay, I will simplify this further. This is minus 10 by 3, and this is like k minus k by 2k by 3, k minus 2k by 3. So this is plus k by 3. Okay, simply plus k by 3. Okay, as my k is varying between 0 to 1, right? K is varying between 0 to 1, hence this will always be always negative. Always negative, right? This will always be negative. So if this is always negative, what does that mean basically? If this is always negative, this means that I have a sign change. This is positive, this is positive, this is negative, and again, right, this is varying from 0 to 1, so this is 10 plus something positive, so this is positive again. Hence I have again, right, no sign change. Here I have one sign change, here I have one sign change. So one sign change and one sign change. So I have two sign changes, hence total so two sign changes, right? Two sign changes, hence two closed loop poles on the right hand side of S plane, right? So two closed loop on the right hand side of this plane. So answer will be 2. So from here we can check, right? Answer will be 2. Okay, simple. So this was basically it for this question. Now let's solve the next question basically. So what is the next question telling us? So next question, we have been given the Nyquist plot of a stable transfer function. So whenever they give you right stable transfer function, that means of g of s, they are telling stable transfer function g of s. That means what? My poles of the g of s are on the right hand side are 0. Okay, so I'll write this information down as I'm reading. I try to decode things, right? So from the question itself, I can say that p plus ol equals 0. It has told us that it is stable OLTF. This is fine. Now we are interested in the stability of closed loop system. That is okay. Now we've been given this what Nyquist plot, right? Nyquist plot is given, okay, and this has given that this is a unity feedback system. That is also fine. Now it is asking us which of the following statements are true, right, or is true. This was a GATE 2009 question. Then MSQ wasn't there, so is true. Only one option will be correct. And also it is asking about the gain and phase margin. So this will also revise you the concept of gain and phase margin also. So how to solve this? So what you will do this is first you have to understand about, like, read the options. You can eliminate the options, and from there also you can understand which options are true or not true. This is telling us g of s is an all pass filter. So if g of s is an all pass filter, so you will study this in analog circuits, that for all pass filter the magnitude response is constant and the phase response is like it rotates a whole circle. It is correct that yeah, phase is rotating a whole circle, that is correct, but the magnitude should remain constant. Is the magnitude here constant? You might say yes sir, this is circle magnitude is constant, radius is constant, but radius from where? From its center. But from where do I measure the magnitude? I measure the distance from the origin, right? That's how I measure the magnitude of any uh, any function, right? If I'm plotting it in the real and imaginary axis. From the origin, the magnitude is happening what? Here the magnitude is increasing, and then again, like here it is maximum, then it is starting to decrease here, right? Starting to decrease. Here it is minimum, and then again it is increasing. Okay, so magnitude is changing. Okay, you will study this in all analog circuits. Here, there you will study different types of filter, right? So also for all pass filters, my pole zeros are in the symmetrical location. Pole zero in the symmetrical location. That's why my magnitude is same, constant, and other things phase changes, right? So eliminating options. So in this case, right, you have to read obviously all the options, then only you can understand. Or if you directly solve the question, right, MSQ comes, then you have to obviously read all the options. But if you directly solve the question using Nyquist, only one option will be correct, and you will find out that yes, this was very easy, only that option is correct. But if you don't want to use that option, right, then you have to use this, right? So you have to obviously, if MSQ has came up, then obviously you have to read all the options. So for option A, we know magnitude response. Here, right, do keep that in mind. The g of it is talking about the g of s. It is commenting about the g of s and not about the closed loop system. It is only talking about the open loop system. So we will comment about the open loop system, right? So magnitude response is constant. Okay, for all pass filters. But not constant, but here it is not constant basically. So this is one thing. So hence option A is eliminated. So this is gone. Okay, what about option B? Option B will come, right? Basically g of s has 0 in the right half plane. So we have to check this one, if g of s has 0 on the right half plane. So for that we can use Nyquist, right? We can use Nyquist because we don't have the g of s. Okay, we don't have the g of s given in terms of s, right? So we can't use Routh, we'll simply use the Nyquist. So it's talking about g of s has 0 in the right half plane. Now if it is talking like that, then obviously it is talking about the 0 of g of s, not of 1 plus g of s. So simply you will see the encirclement around the origin, okay, not around the minus 1 comma 0 point. So they have given the both points, just be careful, you will see the encirclement around the origin, right? And Nyquist contour is not given, okay, we'll assume it is clockwise. If some error arises, right, then we'll assume the opposite direction. So for B, what we'll do, simply we have to find the, like, stable OLT is given, so P plus OL is 0. Okay, now if P plus OL is 0, right, P plus OL is 0, we need to comment about the open loop zeros. So we'll comment about the encirclement on the origin minus Z plus OL. Now we're assuming clockwise direction of Nyquist contour. Okay, Nyquist contour. Okay, if we're assuming this, right, if we're assuming this, then what does this mean? This means that we have one encirclement around the origin in the clockwise direction. So n equals to 1 in the clockwise direction, but obviously this should be in the anti-clockwise direction, opposite of the Nyquist contour. So it is minus 1, right, minus 1 in the clockwise direction, because I'm expecting anti-clockwise as positive direction, right? So this will be minus 1 equals 0 minus Z plus OL. So Z plus is coming positive, so hence there is no error in our assumption. So equals to 1. So we have 1 right hand 0. Right hand 0. So obviously from here we can say, right, option B is correct, and we can move on to other question. But let's just stay in this question and check the other options as well, right? Can we eliminate the other options as well? So like if you are in a state of confusion or something, right, whenever you are in a state of confusion, so what you do is basically you try to, like, you don't know if this option is sure or not, you try to eliminate the other options. Okay, so here is telling us g of s is the impedance of a passive network. So what do you mean by passive network? Passive network should have its poles and zeros on the left hand side of my s plane. Okay, in active network, poles and zero can lie on the right hand side of my s plane, but this can't be possible. Okay, passive network will always have its poles and zero lie on the left hand side of my s plane. Okay, right hand zero is not possible. So you will study this in analog circuits, right? Active networks, passive networks. Like you have studied network theory about passive and active networks, but with poles and zeros you haven't studied. That you will study in the analog circuit course. Okay, so this is about the passive network, and now as we have 1 0 on the right hand side, hence this option is not correct, as we have 1 0 on the right hand side. So this option is not correct. And what about the D? What is D telling us? D is telling that g of s is marginally stable. Obviously g of s is marginally stable, g of s is stable. The question has given stable transformation. How can g of s be marginally stable? Okay, so g of s is stable. In the question itself it is given, right? type of question basically given. So again we're back with the gate question. So again, like this has come up in gate, right? This has come up in gate. Similar type of question. The number of times the Nyquist plot g of s equals to s minus 1 s plus 1 will encircle the origin in the clockwise direction. Now what is the difference here? There it was telling me will encircle the minus 1 comma 0 point. Now what is it telling me here? It is telling me when it will encircle the origin. Now if it is telling me about the origin, so I will only care about the OLTF, will not care about the 1 plus g of s, right? Okay, that's why if it would have asked about minus 1 comma 0, then I have to write 1 plus g of s, right? Okay, so simple, we'll use that formula. Okay, we'll use this formula n 0 comma 0, and it has also mentioned that it hasn't mentioned anything about the Nyquist contour. So first thing is we will assume, like that is a general convention, assume contour in the clockwise direction. Now if we assume Nyquist contour in the clockwise direction, what does that mean? That means this encirclement will be in the anti-clockwise direction, and the formula will be p plus ol minus z plus ol, right? So formula is like this. So what is my p plus? So my transfer function is like this, right? So what I can observe, so let me just copy the Nyquist contour again, not this one, the previous one. I can simply paste this, I think. Can I or can I not? Yes, I can. So again, this is the Nyquist contour, right? This is the Nyquist contour, and I can see that I have a pole on the left hand side, and I have a 1 0 at the right hand side. 1 0 is at the right hand side. So here I have 1 0 at the right hand side, right? So if 1 0 is at the right hand side, so my z plus ol equals to 1 and my p plus ol equals to 0. Okay, so n 0 comma 0 anti-clockwise 0 minus 1 equals to minus 1, right? So it is minus 1 in what direction? In anti-clockwise direction. But obviously the question also asked, right, in clockwise direction. They know, right? So obviously minus 1 anti-clockwise means 1 clockwise, right? 1 clockwise direction, right? So yeah, very simple question, right? Very simple question. So you can solve Nyquist question in seconds. Like if you have to find from plot. Now if they have asked you to find the stability, and if the OLTF is given, right, and they want to find you the stability, okay, you don't draw the Nyquist plot. Okay, you don't draw the Nyquist plot. You just simply find the stability. I will tell you, right? So that is the one thing. Else Nyquist questions are very easy to solve, and you can solve it very quickly. Just that simple concept is there, right? N minus p. But n minus p of what? That is the most confusing part. So you have to understand that, right? Now let's go to the next question. Basically, the polar plot of an open loop system, stable. What does this mean? If it is telling me open loop stable system, this means the OLTF has its pole on the left hand side of S plane. All the poles are lying on the left hand side of S plane. I will write this. Now the closed loop system is, now it has given us the OLTF is always stable and the polar plot is given. Now it is asking us about the closed loop system. So how can I totally sure short comment about the closed loop? It is not asking about relative stability. It is asking about absolute stability, right? So how to comment about that? So what we can do is, first, what does open loop stability mean? Open loop stable system basically means that all poles of OLTF lie on the left hand side of S plane. Okay, this is what basically this means, right? Okay, now what other information can we get from this polar plot? Basically, okay, we have done this polar plot multiple times, right? Similar like this polar plot. What information can we get? This is starting omega equals 0, and the starting represents what type, right? Here what I see, like this is starting from minus 90 degrees, right? So this is type 1, because when there is one pole at the origin, then if I put s equals to 0, other angles become 0, whatever the order is, I don't care. Just that one pole will remain, and that will contribute to minus 90. So all this, I think you are grasping it over, right? All this I have explained very slowly in the polar plot video and in the Nyquist also, right? So this is type 1 system. From polar plot we can observe that type 1 system. Okay, first thing, what is the next thing? It is ending at what? Angle at minus 270 degrees. Okay, or what you can say is like magnitude is 0 and ending at minus 270 degrees. So the order is 3, right? Starting is minus 90 and ending at 270. So I think you are recalling few things, right? In polar plot, what happens when it's starting at minus 90 and ending at 270, minus 270 basically. So yeah, its order is 3. Okay, because 3 times minus 90 is 270. That's why order is 3. I won't elaborate here much further. So this is already covered in polar plot. So order is 3. Why is order important? I will explain it. Also, like we'll assume, okay, we'll assume that it is only consisting of poles. So this is one thing, we'll assume that it is only consisting of poles, right? Not zeros. Positive has only poles. So this is what we have to assume, right? Even if we don't assume, it doesn't matter, because why we have to assume? Because to find the number of what? Zero magnitude semicircle, what we used to do, we used to basically find the number of poles minus number of zeros, open loop poles minus open loop zeros. But here nothing is mentioned about the zeros. So, or what you can do, at the end it is ending at here, right? So this means basically I have at least at the end as tending to infinity, p minus z will be 3, because like all the angles will get cancelled out, right? Basically whatever number of zeros I have, let's say, I will tell you, let's say I have like this, s tau 1 plus 1, then s tau 2 plus 1, s tau 3 plus 1, then s I have. Now this is like order 3, but here, right, if you put s equals to infinity, my angle doesn't go to minus 270, it goes to minus 180. So I have to add another pole, s tau 4 plus 1, right? If I add another pole, what happens? My angle goes to minus 270. So at the end, p minus z itself is 3. P minus z itself is 3. So from here also we can understand that p minus z will be 3 itself. Okay, p minus z will be 3 itself. So my p minus z is 3. Okay, p minus z is 3. Like if you assume no zeros, okay, or you can do p minus z equals 3 itself. That also you can do. Assume no open loop zeros. Okay, so if we do that, basically what I can say, p minus z equals to 3. So 3 semicircles of 0 radius. Now how am I writing this? All this I have explained, right? Of 0 radius in what direction? Like it is p minus z, right? Obviously it will be in the anti-clockwise direction, right? Anti-clockwise direction. Okay, here, right, it is type 1 system. So one semicircle of infinite radius in what? In clockwise direction. Okay, in clockwise direction. Okay, so as like there, obviously it was going in the anti-clockwise direction, right? Anti-clockwise, because around the 0 we avoided the 0 contour, right? This contour, I hope you remember, right? We avoided this contour, so it was going in the from minus pi by 2 to pi by 2. Okay, if you can't recall, just draw the contour. It was going from minus pi by 2 to pi by 2. Hence here it will go from pi by 2 to minus pi by 2, right? So yeah, let me just hold on a second, right? So yeah, sorry for the interruption. Basically, like I have like one call came up, important call. So now, right, what we can understand is like all this we understand, like the other things we understand. we needed 4 curves, right? One curve is already given, polar plot. The other curve is mirror curve, inverse polar plot, which will be from this polar plot itself, mirror image of this one. And the other 2 curves were the infinite radius circles and the zero radius circle. Zero radius circle I got from here, right? From the p minus z information. I told you how to derive it, right? And the type we got from this one semicircle of the rays. Obviously, we'll assume no open loop zeros. We'll assume this no open loop zeros, right? Like even if you don't assume, then also your p minus z will always be 3. Okay, that is understood. So let's draw the polar Nyquist plot basically. Have I drawn it? No. Imagine of geometry surface, right? So now, like, what is my polar plot? Polar plot is something like this, right? Okay, so this is my polar plot. This is my omega equals to 0, and this is my omega equals to infinity. So I will not, I'll write it later. Let me complete the inverse polar plot. So the inverse polar plot will basically something like this, and we have one infinite radius half circle, right? So it will be obviously like I told you, right, from where it starts and where it ends. It starts from this inverse polar plot, right, and ends at this uh, normal polar plot, right, at 0 plus basically. So this is omega equals to 0 plus, and we know it is in the clockwise direction. From there also we can understand that it is in the clockwise direction. So it will be something like this. Okay, and what about my 0 radius circle? 0 radius, I had 3, right? 3 0 radius. So I'll have to delete a bit of here. Obviously that is for just representation. It doesn't matter, the 0 radius, right? It doesn't matter. Okay, so basically it will be something like this. It is in the like this is in the clockwise, so it is in the anti-clockwise direction, right? And it is starting from where? So what happens to the theta is from plus pi by 2 to minus pi by 2. Here it becomes 3 pi by 2, like minus 3 pi by 2 to plus 3 pi by 2. So minus 3 pi by 2, minus 3 pi by 2 is where? This is pi 2 minus this minus pi, this is minus 3 pi. So it starts from this angle and it goes in the anti-clockwise direction, right? So if I just draw it, it's ends, oh no, not here, it comes to circle here, it ends around here, right? And this one starts around here. Okay, it doesn't matter actually much. This one starts around there. Okay, so yeah, like my polar plot goes like this, it goes like this, then it goes like this. Okay, then it goes like this, and it goes like this and like this, right? So basically what is this point? This point is omega equals to infinity plus. What is this point? This point is omega equals to infinity minus, and this point, right, this point is omega equals to 0 minus basically. So it starts from this 0 minus point and like ends to this 0 plus point, right? I have told this in like one of the short notes. If I just go back to there, so that like every concept is getting used to show you that every concept is getting used, right? Where was it? Yeah, starts from where my mirror image ends. Basically, where does mirror image end? At omega equals to 0 minus it. That's where my mirror image has ended, and ends where my actual polar plot starts. Okay, I hope you understand this. So yeah. So where is it? So this is this. Yeah, this is the polar plot basically. Now what is this point? This point they have given us very clearly, right? This is minus 1.42, the point where they are crossing each other, right, at the on the real axis. So this point is minus 1.42. So this will decide everything basically. Minus 1.42, right? And my minus 1 comma 0 point will lie somewhere around here. Minus 1 comma 0 point will lie somewhere around here, right? So now this is the critical point. Obviously, they are asking about the stability, right? So what information we know? Information we know that P plus of OL equals to 0. This one we know, which is equals to P plus of 1 by OL, right? That we know. Now obviously we have to find about the stability, comment about the stability. So we have to find the Z plus, right? Z plus of 1 plus OL. Now we have to find the encirclement around the minus 1 comma 0, right, for stability basically. So what we'll do, how many encirclements are there? So obviously I'm assuming a clockwise Nyquist contour. They haven't given us anything, so I'm assuming a clockwise Nyquist contour, right? So that is first thing. So should have written it here. So if not, it is not written, obviously by default we consider clockwise Nyquist contour. This is by default, right? So if you consider clockwise Nyquist contour, what does that mean? That means like my number of encirclements should be anti-clockwise. That is a positive one, right? So this is one in the clockwise direction, one encirclement in the clockwise direction, another encirclement in the clockwise direction. So I'm getting n equals to minus 2, right? N equals to you can say n equals to minus 2 in the anti-clockwise direction, or n equals to 2 in the clockwise. But as I am expecting in anti-clockwise, right, this is my positive sense, so I will write n equals to minus 2 because I'm writing p minus z, right? So that is what I will write. So minus 2 equals to, so right, that is a simple formula. What formula am I using? It is n minus 1 comma 0 equals to p plus of 1 plus OL minus z plus of 1 plus OL. Okay, so this, right, this becomes p plus of 1 plus OL. What is p plus of 1 plus OL? P plus of 1 plus OL is basically, what is it? It is 0. Why am I laughing? So yeah, didn't have enough sleep. So this is 0. And what is z plus of 1 plus OL? Z plus of 1 plus OL is what is we need to find basically. So this is z plus of 1 plus OL. These are the closed loop poles. So here, right, I can get that z plus of 1 plus OL equals to 2, right? 2. So I have two right hand poles, right? Closed loop poles. Like that means my system is unstable. System is basically unstable, right? Just hold on a second. Yeah, system is system is unstable, right? System is unstable. So which option will be correct? It is unstable with one pole on the right hand side of the span, unstable with two poles on the right hand side of the span. D option is correct, right? So here we wouldn't have been able to use the Routh. Okay, we wouldn't have been able to use the Routh-Hurwitz criteria. Now, for example, let's say if this plot was also given and plot and OLTF is also given, if both is given, right? If both of them are given, then what does this means? This means basically that we can use the Routh-Hurwitz criteria, right? Use Routh-Hurwitz, okay? Simple Routh-Hurwitz. If it is a third order, you can solve it in seconds, right? So use Routh-Hurwitz and you will do it much better if you are comfortable with that, okay? So if you are not comfortable with Nyquist, because in Nyquist you have to plot and then do other things, right? So if you are comfortable with this, you can use Routh-Hurwitz criteria, right? So use, okay, by RH you might think this is right hand, so no, use Routh, that you can use, right? So yeah, that is what I'm telling. I will show you if some example is also here, right? Now this is the next question. So in this question, what you have to do, like they have given the polar diagram is given, that is in the next page, but let's read, of a conditionally stable system. Conditionally means it depends on some condition, right? Whether it will be stable or unstable, okay? That's what condition means. And which condition it depends, here it is given, right? So we'll read the question. So the polar diagram of a conditionally stable system for open loop gain of k equals to 1 is shown in the figure, okay? Polar plot for k equals to 1, open loop gain, basically the system parameter, right? So like how is my OLTF defined? OLTF is defined like this, right? So I will write this, OLTF equals to k into g of s into h of s, okay? And I'm varying k, okay? And like k equals to 1 is g of s into h of s simply. So I'm varying k and this plot is getting varied. How is it getting varied? What is it getting varied? I will explain everything, right? So the polar plot for k equals to 1 is given, okay? The open loop transfer function of the system is known to be stable. If the open loop transfer function of the system is known to be stable, then what I can decode that my p plus of OL equals to 0, okay? The right hand side of the open loop poles are 0, okay? That I can decode. And the closed loop system is stable forward. The closed loop system is stable forward. So for what condition my closed loop system will be stable? For that I have to find out few conditions. So with the help of Nyquist plot I can find. First let me complete the obviously Nyquist plot, because it's only the half part, the polar plot is given, right? Only the polar plot is given. Like what I can observe is this again a type 1 order 3 system, right? So again, right, what will happen, that there are zeros also, you can see, right, there are zeros also here, but at the end what is happening, p minus z becomes this 3 only, right? So this 0 is contributing some positive angle, right? Okay, as I explained in polar plot, what happens, like if there is some 0, so it contributes some positive angle, then again this dominance of the 0 is over and the pole again dominates, right? Hence we are ending at minus 270. So I explained, right, in the previous example with that, but at the end my p minus z will be simply what, p minus z will be 3, as I explained with the example. So here, right, how many half circles will I have? The number of half circles of 0 radius will be what, 3, right? See, and number of infinite radius half semicircles will be what, will be 1, because this is a type 1 system. This is starting from here, right? Type 1 system. Sorry, like in the question it should be mentioned that this is omega equals to 0, like this is understood, still they should be mentioned this is omega equals to 0 and this is omega equals to infinity plus, okay? Omega 0 plus and infinity plus, okay? So this is the case. Now let's complete the polar plot basically. So I'll just draw the mirror image. This, oh no, this will be difficult. Everything is difficult nowadays. So this is the polar plot. Now I'll just keep this one here. Just understand that this is the intersection of these two. Okay, and it goes like this. Have you understanding why is this like this? We have a 0 here, right? That's why. So yeah, this also you should be able to comprehend. We have studied this so well in polar plot. This also you should be able to comprehend it. So this is like this. Oh no, this will not go away. Shit. This will. Oh, why is this together? I don't understand. Now it is. This is this. And this is this is going like this, so it is basically going here, and we have what, three uh zero radius semicircles, right? Which is starting from where? Again, it is starting from what, minus pi by 2, minus 3 pi by 2, right? So it is starting from here. Okay, basically where my polar plot ends, right? Basically where my polar plot ends, it starts, and where my mirror image starts, right, it ends. So it's the opposite of the previous one, right? No, where my polar plot ends, I'm sorry. So it will be something like this, right? So it will be starting from minus pi by 2, and it is in the anti-clockwise direction. So this is one half circle, and this is two half circle. Okay, I may have drawn the previous one incorrectly. Okay, sorry for that. 1 3, yeah, it will be something like this. Sorry, I may have drawn the previous half circle incorrectly. Even it doesn't matter that much, but this here it was three half circle. I only drawn like one half circle. Okay, so the one and a half circle, so it went wrong there. Okay, I have to delete this. Let me draw the axis first. This is two half circle, and this is third half circle, right? So it is ending where? It should end. No, this is third half circle. It should end here, right? It should end at minus plus 3 pi by 2. What is plus 3 pi by 2? Basically pi by 2, pi, and plus 3 pi by 2. So yeah, that's why I was doing it wrong. That's why I was thinking something is wrong, right? Something is wrong. So rotating like this, right? And ending here. Okay. So yeah, this is like this. Yeah, that is it. And here also it will end here, right? And here, right, my where my mirror image of polar plot ends. Okay, it goes like this. So this will be in the anti-clockwise direction, right? Here I have the axis. Okay, so it will be something like this. Now the direction of this mirror image will be something like this. Okay, in the clockwise direction. And yeah, this is it, right? So now what should we do? Basically, right, we got all the information. Now these are my critical points. Basically, let me mark the critical points. This is one of the critical point, this is one of the critical point, this is one of the critical point, right? They have given us 3 points. Okay, so let me mark them, like I will mark them differently. But first let me like, now what is the question asking? Question asking is when is it stable for different values of k. Okay, so I have to vary k and see when is it stable. So when will it be stable? When will it be stable? It has told us that POL plus is 0. Okay, if POL plus is 0, this means P plus of 1 plus OL is also 0, right? If P plus of 1 plus OL is also 0, what does this mean? This means basically that my n around minus 1 comma 0 in which direction? In anti-clockwise direction, basically has to be minus z of minus z of 1 plus OL, right? Now for stability, for stability obviously 0 has to be like this, z plus 1 plus OL has to be 0 as it represents the closed loop poles. Stability, okay, as it represents the closed loop poles. What does this mean? So n of minus 1 comma 0 has to be 0. Okay, it has to be 0 for stability, for closed loop stability. Okay, so now from here, when is my number of encirclements 0? Like I will obviously cross through this real axis, right, and I will see where is my number of encirclements 0. If I am at this point, how many is the number of encirclements? If I at this point, my number of encirclements 1 and 2, right, in the clockwise direction, it is minus 2, but still it is not 0. Okay, so in this region, okay, I will just copy this one because I don't want to mess around with this one. Oh no, in this region, right, in this region n is not equals to 0. Okay, now what about this region? In this region n is equals to what? One anti-clockwise encirclement and another clockwise encirclement, right? So what we can see in this region, number of encirclement is 0. So if my critical point lies within this region, then my system will be stable. So somehow my critical point should lie in this region. That is what I am trying to find out, because I have to find the range, right? I have to find the range. So in this region, number of encirclement is 0. Okay, if my critical point lies in this region, right, that is what I am trying to explain. If my critical point lies within its region between minus 2 to minus 0.2, then it will be this, but not minus 2 to minus 0.2, because I am varying my k as well. I'm just trying to tell like what is the region, not the exact values. The values will change. I will explain. Right now, if I lie within this region, what will happen? If I lie within this region, basically, what is my n like n one clockwise root encirclement and another clockwise root encirclement, if I lie within this region. So here also my n is in 0, right, and if I lie within this region on the left hand side, right, on the left hand side, if I lie within this region, then what happens? Obviously I don't have any encirclements, right? So here also my n is 0, so I'm good to go. Here also my n is 0. Okay, so if my critical, if I by I lie in this region, I mean that if my critical point lie in this region or in this region, if my critical point, so somehow I have to make my critical point in this region or in this region for my system to be stable. So I will name this regions, right? Let's name this region as A. Okay, let's name this region as B. Okay, I will color this differently. What should I color? What should I color? What should I color? Green is also used. Everything is used, man. I should use white. Let's name this region as A, B, then this C, okay, C, and this D. Okay, so what I'm observing is like those are not exact values. Exact values will change. So just let me solve the question, you'll understand. If I lie within region A and what? C, if I, not I, now I will say if my critical point minus 1 comma 0 lies within region A and C, then n is 0, hence system will be stable out, right? Hence system will be stable. Okay, this is the first case. Basically this is the first case, right? So if my system is stable, what does this mean? So like this means system is stable, so like my poles will lie on the left hand side, right, closed loop poles. So how will I make my critical point lie in this region? So what is the value of my critical point? So value of my critical point is what? Minus 1 comma 0, right? Okay, those are the coordinates. So it is basically minus 1. Okay, so basically what I'm varying this g of s of s, right? G of s of s, right? So here the value, the magnitude of g of h of s at this particular frequency, right? It is what? Minus 8. It is minus 8. So I want to vary it further. So I am in this region. I'm in this region, right? So I want, like, what do we observe? So this is the plot of what? G of h of s. This is the plot of g of h of s. Now, what are the values here? So this point value as minus 2. What does that mean? What does that mean? So for that particular frequency, this point value is minus 2. So initially I mentioned, right, my OLTF is kg of s. So if my k is 1, then this point is minus 2. Let's say if my k is 2, what happens? If my k is 2, what happens? Simply it will get scaled by 2, right? It will get scaled by 2. So this minus 2 point will be minus 4. Like this intersection point will become minus 4. Simply scaled. As my k is 1, so g of h of s is minus 2 at this state. Now if I make my k 2, then k times g of h of s is the magnitude, right? K times g of h of s is the magnitude, right? K times g of h of s is the magnitude. Now g of h of s has value 2, magnitude is 2. I'm multiplying a 2, then what happens? This becomes minus 4, right? This becomes, magnitude becomes doubles, magnitude doubles. So everything is scaled, right? So everything is scaled by k. The plot will be scaled by k. The plot will be scaled by k. So I can simply scale the plot by k. So what I will do, I will just write here these different regions as k, right? Functions of k. It will be similar for easier for me to understand. So this region of the two intersections is minus 0.2 k. Okay, let me write this in white color or some, okay, because this is confusing again. And this is minus 2k, right? And this is minus 8k, right? So if my k is 1, so yeah, this is fine. This is like previous one as showed in the question. If my k is 2, what will happen? Everything will get scaled by 2. Everything will get scaled by 2. So everything will shift to this side, right? If my k is 2, okay. If my k is 0.5, it will try to die down. If my k is 0, if my k is 0, what does that mean? If my k is 0, obviously I don't have any plot. So everything will go down to here, right? Everything will go down to origin. So from this analogy is also, you can, I hope you get it, right? What happens if my k varies to the extreme ends? So k becomes 0, this went to this here, right? Goes to origin. If k increases, this also becomes bigger, right? Bigger, magnitude becomes bigger, okay? That's why this expands. This expands. So I have get it. Now, what is this region? This region is basically, what is the value of this region? Minus 8. So minus 8k, right? So if my critical point lies within this region, then it is fine. So I want E. What is the A region? A region is basically from minus 8k. Okay. Now my A region basically lies minus 8k to what? Minus infinity, right? And what about my C region? C region lies between which two? Between this minus 0.2k to minus 2k to minus 0.2k. So minus 2k to minus 0.2k, right? Okay. So this is what my C region lies. So now what happens? So basically what you can do, I want this A value to be C and to be critical point, right? So critical point should lie in this region. So I will change this with A with critical point basically. So minus 1 should be less than minus 8k, right? Okay, this is the first condition. So k, okay, what I will do, I will simply multiply minus on both sides, or I can swap, I can make my 8k in this right hand side and take this minus on the left hand side. So this will become plus 8k and this one will become plus 1, but this sign will interchange, right? Like this flow of inequality will interchange, or if you multiply both sides with minus 1, then also this flow of inequality changes. So this one will become k less than 1 by 8, right? So this is the first condition, right? My k has to be less than 1 by 8 basically. Okay, so if my k is less than 1 by 8, then my system will be stable. Not talking about the infinity case, because infinity is not given. Okay, infinity is not given in the options, as you can see, right? infinity is not given, right? So infinity is not given. Now what about the other case, right? The C case. So first I will solve this one. Minus 2k less than minus 1. So I will again multiply with minus 1 on both sides. This will be k greater than half. And what about this one? This is simply minus 0.2k greater than minus 1, right? Again multiply both ends by half. So this is basically k by 5 equals to 1. So k has to be less than 5. So k greater than 1 by 2 and less than 5 is another condition. So these are my two conditions, k less than 1 by 8 and k lie between less than 5 and half, right? So these are basically what my two conditions represent. So is there any option present? So it is between half and 5, okay, half and 5, and it is less than 1 by 8, right? So these are the options, right? Less than 1. So option B is the correct option here. So yeah, this is very good question. Okay, if you didn't understand it, we can solve it in other ways also. You just go to the different points, right? Different points and check for stability on the edge cases. On the edge cases, put k equals to 1 by 8, put k equals to half, 5. You check the edge cases and you will see different stability. But this is the most efficient way in which you can solve this question, okay, in the best manner, what I can think, right? So this is the most efficient way. So this is very simple question, okay. Just read this question and try to solve it by yourself. What is this telling us? The frequency response of a linear system g of j omega, basically unity feedback system, is provided in the tabular form, okay. So like the angle and the magnitude is provided for various frequencies, right? So the gain margin and phase margin of the system. So again, right, what is the definition of gain margin? What is the definition of gain margin? Definition of gain margin is basically the margin that is required when my phase is minus 20 degrees. So, or you can say the inverse of my magnitude, okay, in absolute scale, okay, normal scale. In log scale, it is the margin you have to add, right? So here is my phase minus 20 degrees and this is my gain. So inverse of this one is 2. So let's solve this basically. So gain margin omega p into h of g omega p, okay. So it is 1 divided by 0.5, so it is equals to 2. It is equals to 2, right? So if it is equals to, now what is, like, you have to find it in dBs because the options are present in dBs itself, right? Not in normal units. So gm in dBs, right? Twenty log 2, and log 2 you should remember that it is 0.3, right? Log 2 is 0.3, like log base 10 2 is 0.3. You have to remember this because this one will come hundreds of time, right? So this is, if it this is 0.3, so this will come out to be 6 dBs, okay, 6 dBs. So first one is okay, 6 dBs is okay, right? And gain margin is positive, okay. I can see gain margin is positive. Why? Because like from here also I can see that this is the point where my gain is 1. So this is my gain crossover frequency and this is my phase crossover frequency. So my gain crossover frequency occurs earlier than phase crossover frequency. So my gain margin will obviously be positive. So yeah, my gain margin will obviously be positive and my phase margin will also be positive. So like what is phase margin? The amount of margin, that the amount of phase lag that I need to add when my gain is 1, right? So how much phase lag I need to add? Phase lag means amount of negative angle I need to add, right? Negative angle I need to add. So this is minus 150 at when my gain is 1. So this minus this is minus 150 when my gain is 1. So I have to add minus 30 degrees with it, right? Minus 30. So what is the amount of phase lag I need to add? I need to add 30 degrees. So 30 degrees is the positive, like is the angle and track, but it is a negative angle. So minus 30 degrees. So phase margin is 30 degrees itself. So don't get confused by that. Don't get confused by that, or simply use the formula. Simply use the formula and you will never get confused. What is the formula for phase margin? Okay. Phase margin is 180 degrees plus g of j omega g into h of j omega g, right? So you will never get confused. Just use the formula and be must, right? Be must. So else you just understand by that the phase concept. So phase margin is how much? This is 180 itself. And what is the angle? Angle is basically minus 150 here. So it will be minus 150. So this is 30 degrees, right? So this is 30 degrees. Obviously my option A is match. Obviously I can say that phase margin and gain margin positive anyways, but still just to prove it to you that yes. So this was very simple, but this may come, right? You might get confused, so that's why I have to take this question. Another question that I have to take, right? This is also another type of question, very simple question, just 1 second question only, but again you might get confused with the terminology, right? So the critical value of gain of a system for a system is 50. Now what does this critical value mean? Just resume, right? What does this critical value of gain means? Just think about it for a second. Again, the system is operating at a gain of 25, but it is saying critical value is 50, but the system is operating at gain 25. Find the gain margin of the system. Okay, how to find the gain margin of the system? So let me plot a polar plot and explain through there, right? We plot the polar plot. So let's say current gain of system is 25, so it is operating at 25 gain. So this is, let's say, like k desired. So a desired gain for my system I want to operate at k desired. So this, let's say this is the gain. Okay, I will explain everything. Just let me draw 2 curves, and there also we will understand better, right? Oh shit, no. So this is k critical. Now what does this k critical and k desired mean? So what happens if I just multiply this whole thing, right? This is the point, this is the gain at which this is operating. Okay, so let's say my gain of g omega and h of j omega is 1 itself. Okay, I'm just multiply k with this one, right? So multiply k and this will become k, right? So the k is the varying parameter which is varying the gain. Okay, varying the gain. So if I just multiply k with this, obviously it will get expanded. If I multiply like k critical is greater than k desired, then it will get expanded. If I multiply some k which is smaller than this k desired, it will get contracted, right? It will be less. Okay, so I have been understanding. If I multiply something more than 1, it will be more. So what this k critical means? K critical means just the amount of k, the gain that I need to multiply so that it may cross the critical point. That's why this is known as k critical. Critical point is what? Minus 1, 0, right? Minus 1, 0 is the critical point. So it should just cross that. Until before that, it is fine. It is not crossing that point. So the system is stable. Okay, that's why this is known as k desired. So I want my system to be stable. Hence, I make it k desired. Right? So now, like. What I can write? Let me write my g of s, h of s, okay, like this one, k by s tau 1 plus 1 s tau 2 plus 1, right? So here, right, you can see that my gain of my old TF is k itself. All this is fine. Okay, like I mean, like that gain is k, like the main gain is depending on k itself, right? Main gain is depending on k itself. Okay, so if I multiply k, this will be expanded or contracted. Gain varies with k. Okay, obviously if I vary omega, that will vary, but if I keep my omega constant and vary k, gain will vary with k. Okay, and like this is order 3 system. Okay, and ending at this minus 270 degrees, and obviously starting from minus 90, right? So this is this one, right? This is this one. Now what about my question, right? So what is the question asking? Question asking find the gain margin. So from here, can you tell me what is the k desired? K desired is, or you can say k operating, right? Or k operating. In what gain it is operating? It is operating at 25 gain. Okay, so this is operating at 25 gain. And what is the critical value of gain? 50. So if my k critical is 50 and k desired is 25, then how can I find the gain margin? So at this point, like my k, like just write this simple formula. Whatever the omega g, like what does this gain like this phase crossover frequency depend on? Does this phase crossover frequency depend on k? So omega p is not a function of k, right? It is not a function of gain itself. It is only function of uh, like the phase itself, right? Like only the phase, right? So it is not a function of k, not a function of k. So it's not a function of k. So omega p will remain same for both cases, right? Omega p will remain same for both cases. So omega p is like same for both cases. So if my omega p is same for both cases, what can I say? Only the gain margin will change, right? Gain margin will change. So first, this is the, let's say g gain margin will change. Okay, so what I can say, like for this case, right, what is the gain margin? Like if my k is k critical, what is the gain margin? Gain margin is 1 in absolute values, or in dBs it is 0, right? It is 0. Okay, I will say gm operating, right? Gm operating, what is the current gm when the system is operating? Gm operating is so still I have this much distance, right? K desired. So obviously, like the my gm operating will be inverse of this one, right? Inverse of this magnitude of g of g omega p into h of g omega p, right? By 1. And what is this equals to? So simply this will come above, right? I will copy this one. Okay, I haven't put in this one. So this will come at the top. This will be omega p tau. Okay, this will be magnitude. So omega p tau square plus 1, right? And this is divided by k desired, basically k desired, right? So this time my k value is k desired, right? So this is asking my gain margin of system. Okay, this is basically asking the gain margin at which my system is at with the gain at which it is operating. So I have to find this gm operating. How to find this one? We'll find this one, right? Now what about my gm critical? Gm critical value I know, right? It is equals to 1 itself. Why? Because like here obviously it is crossing the -1 point, a critical point at when it is crossing the negative real axis. That is why this is known as k critical. Definition of k critical itself means that gm should be 1. Okay, it is crossing my negative real axis at the critical point. That is the definition of my k critical. Just keep this in your head, right? So this one, this is equals to 1, but my phase crossover frequency isn't changing, right? It's still same. So the this numerator will be same, but the denominator will change. This will be k critical this time. Okay, I'll just mark this one as red and this one as green. Okay, I'll just take another page. So now, right, I will just take the ratio of these two, gm operating and like gm critical. So gm operating and gm critical is 1 itself. So we'll get only gm operating itself, which I will write simple gm because that is the gm of the system, right? Not like this. Have I put the mod sign? Okay, I shouldn't have put the mod sign. Sorry about that. So yeah, gm should be equal to the ratio of these two. So what is the ratio? So this is like this one will get cancelled, right? So k critical will go above and k desired will be at the bottom. Okay, k critical and k desired. Okay, so this has different names also. So this is the formula, right? Just remember this, right? if you can remember, or I have derived to you that how to derive it, right? So like this k critical is also known as my k critical, like these are just names, right? Nothing else. K marginal, okay, because like it's just marginally stable, that's why. Okay, and this k desired is known as k operating, right, as I mentioned earlier. So just be careful of that. This is just a terminology, okay, don't get confused by this. Okay, so like from here I can simply use the formula. What is k critical? K critical is simply uh what is k critical? K critical is 50, right? And what is k operating? 25. So 50 upon 25 is 2, right? Hence, like I can say, like only from I have only gain margin, right? I don't have phase margin. So from this I can comment, like if I want to comment, it can be stable, right? But as I don't have phase margin, I should not comment. And what are my gain margin in dBs? Gain margin in dBs, obviously. I told you to remember, right? This will be 6 dBs, right? 20 log 2 base 10 2 is 6 dBs. Okay. So this is a GATE 2018 question. In this question, they have asked for a unity feedback control system with forward path transfer function. Now, what does this forward path transfer function means? Basically, what is a forward path? I have explained in like the basic chapter also. What is a forward path? Forward path is like this, right? When you have a block diagram, let me just draw the block diagram. G, and this is H, and here it is coming minus plus. Okay, what do you mean by forward path? Basically we're moving in the forward direction, right? This one. So this is what my forward path is. So forward path transformation is nothing but the OLTF. They're talking about the OLTF. So also from here you can understand that at DC you are not getting any finite gain. Obviously this can't be CLTF, this is OLTF. If you are confused, then you just see this, and from here you can understand that what is he talking about, what is he talking about exactly. So yeah, if you're sometimes confused, then you see the transfer function. So very important, like to understand the terminologies. So here my forward path transfer function, transfer function forward path transfer function means my open loop transfer function, so OLTF. So this is the first doubt that will come into the student's mind. So then this is a bit of doubtful thing. So g of s equals to ks upon s plus 2. So they have told us the peak resonant magnitude mr of the closed loop frequency response. So here also they have mentioned closed loop, right? From here also you can get the hint that this is talking about the open loop response is 2. So a peak resonant they have given 2, the corresponding value of gain key. So they want to they want us to find the value of gain k. So what will be the value of gain k? So first we have, for that we have to write the CLTF from the OLTF. So what is my closed loop transfer function? So my closed loop transfer function, as this has given that they haven't given, okay, they haven't talked about the unity feedback, but assume nothing is mentioned, so we'll assume unity feedback system. So first the unity feedback system. So what is my CLTF will be? So CLTF will be OLTF plus 1 plus OLTF. OLTF plus 1 plus OLTF. So this is for unity feedback. We are assuming unity feedback. So what is the other information that is given? Other information is given of the resonant peak, which is equal to 2. Now what is my CLTF? So I will just simply write it as T of S equals to simply K by S into S plus 2 plus K. Okay, now what is the formula for MR? MR has its formula like this. MR is equals to KCL by sine 2 theta, or you can write it in terms of zeta. I am just more accustomed to this, so I follow this. You can write it 2 zeta into under root 1 minus zeta square. That also you can write. Now what is my KCL? KCL is the gain, like T of 0, the DC gain of the closed loop transformation. So if you put T of 0 here, what do you get? This is going to 0, so K by K is 1 itself. So this will be 1. Now what is sine 2 theta? That is what we need to find out, and MR is given to be 2. Now my sine 2 theta will equals to 1 by 2. From here my 2 theta will be simply what, like what is like half. Sine of what angle gives me half? It is what, 30 degrees. So it is 30 degrees. So theta will be equals to 15 degrees. Now only you are wrong here. Why? Because theta can't be 15 degrees, because if theta is 50 degrees, then cos 15 will be something more than 1 by root 2. Zeta, the value of zeta will be something more than 1 by root 2. As I mentioned here, right? Theta, range of theta will lie between 45 degrees and 90 degrees. It can't go below 45 degrees. It can't go above 90 degrees. So what went wrong here? So whenever we solve, right, 99% chance is there that we won't write this 2 theta directly. What was another thing about sine theta? Another thing about sine theta was sine 180 minus theta equals to sine theta. So this is what my sine theta was. So this is the relation of sine theta. If you remember, recall it correctly. Sine 180 minus theta is sine theta itself. So here if you see, like let's assume this is theta and let's assume this is 180 minus theta. So this is going a full cycle, and like my maximum value is 180 itself. It is symmetrical around this theta equals to 90 degree. So obviously whatever theta value we have here, right, this will be also same. So angle can be 180 minus theta as well for the same value. Here let's say this is something 0.7 for the same value. So here we are getting 45 degrees, and here we are getting 135 degrees. Let's say for 0.707. So this is the thing. This is the thing basically. So that is why for sine 180 minus theta equals to sine theta. So we can equate this with another equation also, that 180, and 99% of the cases you have to do this, or you might say, sir, this is too much task. You solve it using that zeta formula. You don't use theta formula. You directly use zeta formula, and from there you will be able to find out. But from there you have to solve the quadratic equation. That will also take an extra step. That's why I use this formula basically. 180 minus 2 theta equals to what was 30. So 2 theta equals to 150. So theta equals to 75. So this time it is correct, because it is lying within the range of 45 degrees and 90 degrees. Also, if you find the zeta, you will see that it is obviously lying within our desired range, which is between 0 to 1 by root 2. So I have already written it down. The value of zeta is, so this is let me mark this on a cross. This is cos 75 259. Okay, so this is 0.259. Now let's just write our standard characteristics equation. What is our standard characteristics equation? It is equals to s square plus 2 zeta omega ns plus omega n square equals to 0. Now here I will obviously replace zeta, but let me first write a characteristic equation of whatever transfer function is given to us. What is given? Basically the denominator is the characteristic equation of the CLTF, right? So this is s square plus 2s plus k equals to 0. Now I'll just compare these. So here 2 equals to 2 zeta omega n and k equals to omega n square. So first I will compare this one. So this is like 1 and 2. So if I compare this one, what do I get? Let me take another, if I can find another color, let me take orange. So 2 zeta omega n equals to 2 itself. Now zeta I know. What is zeta? Zeta is 0.259 into 0.259 into omega n. Omega n is unknown, that I need to find out, and this is equals to 2. So 2 cancels out. So omega n equals to 1 by 0.259, which is almost equals to 3.86 radian per second. Don't mess up with the units. I will just write this in the next page. Now what is the value of k? So the k, I should write here comparing 1 and 2. Let me take this to the next page also. This is too much Genji. Now what is the value of k? So k will be equal to simply omega n square. So it is 3.86 whole square. So 3.86 whole square, it is almost 15. It is almost what, 14.93. okay, it is almost 14.93. so k value is this, and that is what this question has asked us to find. So answer will be 14.93. I will not write it here. Answer will be 14.93. So yeah, very simple question. Like these questions come straightforward only. You have to use the formula, and that's it. Just the theta part you have to take care of, because I'm not using that zeta, right? There also, if you solve the quadratic equation, you will get two solutions. One will be valid and another one will be invalid. Which one will be invalid? Here, if you put cos 15, that one solution you will get over there. That zeta value you will get over there, and that you have to ignore. Why? Because that zeta value will be more than 1 by root 2, basically 0.07. Hence you will ignore that one, and that will be straightforward to you. But here it won't be, because the angle is generally not taught. That's why I have warned you at the very first question itself, that just be careful about that. So this is the first question. Now this is the second question. Now try to pause the video and you can solve it for yourself. The closed loop transfer function of a feedback system is given. The closed loop CLTF is given. Find the resonant peak. It's very simple. We have to find the resonant peak. But what is the problem here? This is a third order system. So you might ask, how can I find the resonant peak for third order system? We have only learned about the second order system. So what we have to use here? We have to use the dominant pole method. How you can use the dominant pole method? Let's see. Like you might ask, sir, we don't even know the location of the root. So first I have to find the location of the roots of this one. Then this one I know. Then I have to compare. Then I can use the dominant pole, right? Just don't use the dominant pole method blindly. So here, what was the dominant pole method talking about? It was talking about the real parts, right? Real parts of the root. Real parts of the root. So This is an underdamped system. That's why this whole concept of resonant peak is coming. Obviously, we can say this is an underdamped system. Like we don't even have to find the roots, as the question is telling us by itself underdamped, so we'll consider underdamped. So what happens in the underdamped? The roots are complex conjugate. Now, if the roots are complex conjugate, what does that mean? That means the roots will lie something like this, and the other root, third root will be here, minus 20. Now, can you tell me, like we have to just compare the real parts for dominant, right? We have to compare the real parts. So, can you tell me where does the real part of these two lie? Can you tell me that? The real part will be here, the summation of these two, because what is this? This is a summation of the roots, negative of summation of the roots. As we sum the roots, what happens? The conjugate, the imaginary part cancels out because they are opposite of each other. They will cancel, and only the real part will be remained, and we have to divide it by 2 also, because that part is getting added twice, isn't it? So if let's say one of the root is a plus jb, another root is a minus jb, and the summation of these roots, right, 2a should be equals to minus 2, the negative of this coefficient, b by a, you remember, right? This is class 10 formula. So a will be equals to minus 1. So here my a is at minus 1. So now if I compare these two poles, so let's name this pole as let's name this as a, let's name this as sp3. So sp3 by a equals to, like we have to compare the magnitudes, obviously magnitudes. So it is 20 by 1 is 20, which is greater than equals to 4, so which is greater than 4 obviously. So obviously we can use the dominant pole concept. We can use the dominant pole concept. So that's why the ratio is more, obviously we can use. Now what is the other thing that we need to take care of? The other thing we need to take care of is we have to approximate it into a second order transfer function. So what we'll do, so what is my transfer function currently? My transfer function currently is this. So my transfer function currently is this. Then what I will do, simply I will just ignore this pole, and that is it. 800 by a square plus 2s plus 40. Now this is wrong. Why? Like if you understood that this is wrong, then this is good. Else if you have forgotten, then this is bad, because in the first chapter all this is taught. So what we should do, we should obviously ignore this left hand pole, we ignore this, but obviously the other parameters should remain unchanged. What were the other parameters? One of the parameters was DC gain. DC gain of this one and this one should be same. What is DC gain of this? DC gain of this is 80, sorry, this is not 40, sorry, yeah, this is 40, is it? Yeah, this is 40, okay. 80 800 by 20 into 400 should be same as this one. Here what is the DC gain? DC gain is 800 by 40 itself. We are missing a 20, so obviously we have to add a 20 also. Okay, just be careful about that. Add a 20 also. So that is how we approximate this one. Now what the question has asked us to find is the resonant peak. Very simple, right? To find the resonant peak, what was the resonant peak? It was simply KCL by sine 2 theta. Now like here, like DC gain is this itself, so we don't even have to approximate this. What you could have done is directly, like if you're in the exam hall and you are in the hurry, obviously you don't need to write all this. This is for explaining all of you. What you do, directly come to this question. Dominant pole concept is applicable. Just by seeing at this, you know dominant pole concept is applicable. So you ignore this one. But before ignoring this one, you find the DC gain. And DC gain, you write it as KCL. What is my KCL? KCL is 800 by 20 into 40, which is equals to 1. So this is equals to 1. So you got your KCL. Now ignore this one. And from here, you find your zeta. And that is it. That is basically it. If you find your zeta, then what is your zeta? zeta equals to I'm confused, sorry, omega n square equals to 40. Sorry, I think there has been some mistake. Sorry. The question, there has been some mistake. Actually, the question, this was supposed to be 64. Sorry. This was supposed to be 64. That is what I am thinking, because omega n, like I made this question and omega n I thought it as 8. So all this will remain same. This one will just become 64. And the DC gain of course will change. And DC gain this time will become, it will become 800 by 20, so which is equals to 440 itself, 40 by 64. So DC gain will become 64. Now omega n square from here will be obviously 64. So omega n will be 8 itself. So here this is not this is not this is simply 64. So this will be 20. This will be 40. So omega n equals to 8 radian per second. 8 radian per second. Now from here can we find out the zeta? What is the zeta? Zeta is 2 zeta omega n equals to this value, right? 2 zeta omega n is this value. So 2 zeta omega n equals to 2. Hence zeta equals to 1 by omega n, which is 1 by 8. Now we got our zeta. So what you can do, you can simply replace. Either you find the theta, from there you find out the value, or what you can do is simply replace it. So my MR will be this 40 by 64, 2 times zeta. Simply this time I am using this formula only, 1 by 8 under root 1 minus zeta square, so 1 by 64, so 63 by 64. So this is 40 divided by 2. Like this I can almost assume as 1. If I almost assume this as 1, so this will be 1 by 4. And then this 4 goes above. This is 160 by 64. So this is almost 2.5 something, 2.5 something. Okay, so like this is how you can approximate, like if you are in a crunch, but obviously I am not in a crunch, so I'm just finding the calculator. Where is my calculator? Just hold on a second. I bought the calculator. So here, right, just this will be almost 2.5 something like that. So this is 63 by 64 under root divided by 8 into 2 into 2. So this is divided into 40 divided by 64. Yeah, 2.52, almost 2.52. So that's what I thought. So this is how you can also approximate, right, on the go. So MR will be 2.52, and that is the answer, I believe. Yeah, resonant peak they have told us to find, so this will be 2.52. So this is the answer for this question. Let's now go to the third question. So in the third question, what they have asked that an underdamped second order system having a transfer function of the form, the transfer function is the standard transfer function, just the DC gain is k, okay, not 1, and the graph is given, the plot is given. We have to find the DC gain of the system and the damping factor of the system. Very simple. Like DC gain from here itself you can understand. The graph they have given, it is 1. DC gain is 1. Like DC gain means the gain at 0 frequency. So DC gain is 1 from plot. DC gain is 1. From plot DC gain is 1. Okay. So the first question is already done. What about my second question? What about my second question? Second question is the damping factor of the system. So what will be the damping factor of the system? So damping factor, basically you have to find 2 zeta omega n s. So for that we can find it through this peak resonant, because omega r isn't given, and we know our peak resonant was function of only damping factor and the closed loop DC gain. DC gain is 1, so we can find the damping factor from this peak resonant. Peak resonant is given as 5. So MR equals to this 5 KCL by sine 2 theta, or you can write directly the damping that formula, but I will write it as sine 2 theta. So KCL is 1 obviously from the previous answer, and I will just write sine 2 theta equals to 1 by 5, which is 0.2. Sine 2 raised 0.2. Now again, right, you will get two solutions. 90% of the cases we take the second solution. First solution is what? 2 theta should be equal to sine inverse 0.2. So what is sine inverse 0.2? Let me just calculate. 0.2 sine inverse 11.54. 11.54 degrees. Now if I divide this with 2, this one is almost 5.77, and this is 180 minus theta 2 theta. 180 minus 2 theta should be equals to again 11.54. Now if I subtract this with 180 and divide this with 2, this one comes out to be 84.23. Okay, just check which is lying in the range and which is not lying in the range. So here we can see that this is not lying in the range, and this is lying in the range, right? So this is correct and this is incorrect. Okay, so 84. So from here we can simply find the damping factor. What is damping factor? Zeta. So that is why we're able to use this formula, right? Because we are in that region of zeta 0 to 1 by root 2. So we are not in any other region. That is why we use this formula. That is why the plot is like this. The plot is like this because my zeta is within the 0 to 1 by root 2 region, damping factor. So yeah, if you write cos theta equals to this, theta, put this on as 5.77, then obviously you will get some other zeta which is greater than under root 2, so which is not our solution. We are not lying on that region. So zeta will be cos of 84.23, which is simply equals to 0.1. So zeta is 0.1. So this is my solution. So this is my answer. This questions are very simple and straightforward. Nothing much to explain. Here, right, this is the last question basically. So here the magnitude of frequency response of an underdamped second order system is 5 at 0 radians per second. So the DC gain or KCL is given as 5, and it peaks to 10 by root 3 at 5 under root 2. So peaks, what does that mean? That means it has given us the resonant peak equals to 10 by root 3. So resonant peak MR equals to 10 by root 3 at 5 by under root 2 radians per second. So the frequency it has given, that means the resonant frequency has been given. Omega R equals to 5 under root 2 radian per second. So resonant frequency has been given. What does that mean? That means that like we just put it in the formula. So what is like from the question, can you do anything? From the question, can you do anything? Options, I mean, what you can do, they have given us a DC gain, right? So if you just put s equals to 0, you check can you eliminate any options. You put s equals to 0 on everything is going to 5. So no, we can't eliminate the options here. Difficult to eliminate the options. So obviously you have to solve using the conventional method. So KCL is 5, and like what is my standard transfer function written as? It is KCL into omega n square divided by s square plus 2 zeta omega ns plus omega n square. So this is what my standard transfer function can be written as. Now KCL is given 5, that is good, but all this I have to find. How will I find it? Obviously with that MR formula. So mr equals to what? KCL by sine 2 theta. Now KCL is given as 5. MR is also given. What is MR? MR is 10 by root 3. So 10 by root 3 equals to 5 by sine 2 theta. So my sine 2 theta will be root 3 by 2. Now obviously this 2 theta can be equals to what? 2 theta can be equals to 60, or 180 minus 2 theta will be equals to 60 degrees. Now which one will you choose? Here theta is coming to be 30 degrees, which is not possible. Theta will lie between 45 to 90 degrees. So this obviously I will take the second solution. So theta is coming to be 60 degrees. So if theta is 60 degrees, then what is my zeta? Zeta is cos 60, which is 1 by 2. So zeta is 1 by 2. Now you know zeta. Now what do you do? You find the resonant. This is the flow basically, because MR has only one dependency, zeta. So you find zeta and then you go to the resonant frequency formula. You can't go to the resonant frequency formula at the start, because for resonant frequency you need to know two things: the natural frequency and the damping factor. And we don't know the natural frequency. That's why we won't use the formula of that one. Resonant frequency first. So this omega r, yeah, sorry for the interruption. So omega r equals to omega n under root 1 minus 2 zeta square. So here what is my omega n? Omega n equals to no, omega n we need to find, and omega r equals to 5 under root 2, and omega n we need to find, and zeta is 1 by 2. So this becomes 1 by 2 itself, because 1 by 4 into 2, 1 by 2 minus 1 by 2, 1 by 2. So omega n becomes 5 radians per second. Okay, you don't even have to put this here. So you don't have to put this here. You can directly check from the options which one is matching. Sorry, not 5, sorry. This is 10, right? This is 10 radians per second. So this was my omega ns. So obviously 10 square is only this one, so obviously only option A will be correct, other option will be incorrect, but still we'll write this in the standard format. So what was my standard format? It was KCL into omega n square 100 divided by s square plus 2 zeta omega ns. Zeta was 1 by 2, so 2 cancels out, and omega n is this 10s plus omega n square 100. So you can see it is exactly matching with this one. So yeah, basically this is it for this lecture, and the next lecture we'll start with the polar plot, and I will just relate few things with the lecture 0, the polar plot, so don't be confused with that. So just relate few things, and this chapter is end. So this chapter doesn't have much weightage, but just remember those two formulas, and this is very simple and straightforward formula. So straightforward chapter, so don't worry about this chapter, right? Just remember those two formula, and how to remember also I have told you, and how to remember those simply just by using the theta formula. That is also much simpler than remembering that one. So yeah, this is it for this lecture, and I will see you in the next lecture. Thank you for watching.